Hello everyone. My name is Géza Kulcsár from Inquiry Labs, which is a Budapest-based Hungarian company aiming at providing innovative solutions in research to the systems engineering community, primarily also looking at other industrial domains. And it is my pleasure to be here on this conference with Manning, a graph data science edition of the Live at Manning series. And I wouldn't even waste more time. I would just directly jump into the matter because I think you already, after reading the title, are pretty curious if language models in the end understand system models. Of course, we will have to start with a clarification of the concepts and notions appearing in this title and this question, which we are after here. So, the first overall question is, how do we, maybe essentially as humans, understand systems at all? How do we interact with them? So the simple answer is that if we want to approach a system that is in maybe a first approximation, a compound thing serving a certain purpose, is that this interaction happens via models. Now, of course, as it has been done in the history of science since ages, this model can be a linguistic one, of course. So here I just included a random word cloud on engineering. So of course, using this conceptual field, practitioners have always been able to give or convey an understanding of systems to their peers. Whereas there are other approaches to this as well, which I just simply call formal for the time being, meaning that one uses something of a systems modeling language or a systems modeling approach to have a formal model of the system representing its constituents in a formalized manner. That's right, but we still have to explore a little bit more. What do we mean when we say we are modeling something? Okay, again, now this can have, building upon this same parallelism, which I have just set up on the previous slide. What a model does mean heavily depends on its context where it's used. So having these two sides of the coin, as in the previous slide, one might say that if by model we mean a language model in the sense that this is used in natural language processing, then what we have is pretty much a numeric representation of a text, of a textual corpus, or maybe even the meaning of a textual corpus, although this notion of a meaning is sometimes disputed. On the other hand, if we are looking at the graph model, and a system model is typically a graph model, by the way, meaning, here the word graph implying that it is the mathematical structure, or it resembles the mathematical structure known as graph. That is, it is essentially a network. My argument is that a graph model is an entity or a structure where the meaning is encoded in its relations. But there's a bit much more to it. We'll see it in a minute. So the field of techniques which we are about to employ and explore here is that of natural language understanding. So without going into details of state of the art of natural language processing in this talk, let us just have a simple take on this here, a simplistic take. As you might be aware of, there's an ongoing revolution in natural language processing techniques, especially when we look at one of its main branches, which has become known as NLU, Natural Language Understanding. The results which are now just flowing in one after the other. The newer and newer results provide better and better solutions for automatically interpreting general text. Here, of course, we should focus a little bit on what do we mean by interpretation. These can be several different tasks. In this talk, we are focusing on the specific task of wanting to retrieve some dedicated, directed piece of information from a bigger context. Now, NLU techniques actually rely on, at least for their machine learning aspect, they have been trained on general documents, that is mixed purpose documents coming from a layman context, let's say. So this means that if the specific input which you want to use NLU for resembles that or corresponds with that typical context where NLU comes from, then you can easily get quality results for your own examples as well. However, as it might sometimes be the case for systems modeling, sometimes there's a specific meaning to the text, which is maybe originally even meant to be understood by the experts only, but then at some stage of the process, you might still want to make that meaning, make those notions more approachable, more accessible, more available. This is what we're after. Another related issue is that some people even claim that even if you take the most successful entry in that catalog of NLU algorithms, which is BERT, I'm pretty sure you have at least heard of it. Some people even claim, and I think rightly claim, that even if we talk about understanding what language models such as BERT does, is not really understanding a meaning, but it's rather just learning the form of the text to an extent that it becomes meaningful as an external representation. So what we are about to offer is of course not a general solution, but a specific take on that, how that semantic bridge can be probably established by combining insights from the system modeling and systems engineering perspective and from the natural language processing perspective. So let me just give you this very simple but correct interpretation of what a system model now is, building upon what I've said. It is a graph with a well-defined meaning. I could have even said formal, but I wanted to avoid this, from a previously fixed technical domain. So there is an additional interpretation to this graph, which is not obvious, which comes from the understanding of a certain domain. I just wanted to give you some background on where this comes from. So this whole field has been known as MBSE, for model-based systems engineering, where one of its main groups defined as the formalized application of modeling to support system requirements, etc., etc. So here the emphasis is on it is a formalized application of modeling. And in turn, there's a standardized language typically underlying such activities, which is called SysML, for Systems Modeling Language. It says this is a general purpose graphical modeling language. Here, graphical also means visual and also means graph-like. For specifying, analyzing, designing, and verifying complex systems. In particular, the language provides, and this is where I put a strong emphasis on, graphical representations. Again, I take it with a double meaning, with a semantic foundation. So there is this meaning implied, and this is what we are about to explore now. So from a more of an actor or stakeholder perspective, what is the challenge which we are facing? A typical workflow in systems modeling would look like you're having some systems engineering artifacts, then you have to have some specific knowledge to query them, which is, so this guy over here, this rules all the landscape. He's like kind of a single point of failure. This guy is inevitable. He has the knowledge to formulate queries to retrieve the relevant pieces of information from that artifact pool. And then once you have them, those are, yeah, pretty much inside a certain ecosystem. Therefore, you have to somehow post-process them if you want. And even if you have created some kind of reports from them, even if you have understood them, because you have to have this particular combination of expertise in modeling and in the domain where the system engineering artifacts come from, the burden of analysis comes back to this very guy. This doesn't have to be one person, but this is one persona behind this whole process. So it is it has a very low level of approachability from the outside. Instead, the vision which we are about to advocate here is that you take, of course, you build on the expertise of a system modeler in the modeling side of this divide, but at some point you might want to enter into the textual domain by, instead of just post-processing and analyzing it within the usual space of MBSE, you're turning your models into textual documents. And then by using NLP or NLU in particular, you are creating a language model representation over which, as to according to the state of the art, you are able to offer analysis capacities to a much larger group of people. So now this is this mixed group of people who might know about the domain, but not necessarily about systems engineering, come into the picture. Technically, we're gonna enter into a short demo pretty soon. We build upon our product called Inquiry Suite, which is offers much more than that. I will not go into details in this talk. This is, generally speaking, a tool to analyze your whole digital thread, which in systems engineering means all those different domains and aspects where your overall engineering data might come together. You combine those, you understand the inner semantics. So this is all about semantics. And on the user side, what Inquiry Suite offers, it offers loads of different front ends where you can interact with it. But a typical example is that you're creating something something web-based, like a Jupyter notebook, which I will also show in the live demo today, and you're then processing your data in an understandable, accessible manner. So this is time to go live. Let me just give you a very brief look into how the original established tooling of this field might look like. So this is where you have your model. This is a, a well-established systems modeling tool. I take an example. This is just a showcase example, publicly available. This is an artificial example of some aspects of an SUV. But let me just switch to my notebook here, which I've prepared. So I'm connecting first to the Inquiry Suite. I will go through these phases rather quickly. What's happening here, if I'm able to choose the model which I want to query interactively from the cloud. So there are collaborative methods to do so. Sorry, we'll have to do it again because I shouldn't have rerun this part. Sorry about that. Let's go ahead. Yeah, some indexing is happening. It gets loaded in the database. Now, if you think of this vision, now we are at the querying part. We are still in the modeling domain, and we are querying the things right now. And after that, we are registering our queries. Okay, we just registered our queries. And based on the queries, now we are generating text. So now we have come to this particular point of model to text generation. I'm going to slow down here a little bit. So what essentially happens is that there are certain aspects of a system model which we want to know of. These are just typical entities of interest for a system model, such as the packages, the overall organization of the data, blocks, so the basic system constituents, values of some properties. So this all gets queried by MBSE means with built-in capabilities of the inquiry suite, but this all gets turned into a dictionary in order to create this bridge to the NLU technology, in this case BERT, which we want to build upon. And okay, so as you see here, there's a querying output, but this is still not processed. So this is what I thought. This is an internal representation of the result of querying, retrieving data. There's still no particular processing happening. And in order to get that kind of vision, which we want to arrive at, now we are turning it into text. So what you're seeing now is a bunch of text representing the hybrid SUV example as a textual corpus. So for example, the model package, this is the container, but contains the transmission block. There is a transmission in the car. The transmission block contains a fuel block type, fuel supply product property. This is still systems modeling lingo, which you see here, but it has already turned into a text, and the actually interesting part comes as we start to see what happens if we want to perform semantic search on it with BERT. So I will go on. I'm just configuring my BERT framework here. This is just technical stuff. I'm building a BERT model. Sometimes it takes a bit longer. I hope it won't take too long. Yes, we are there. So as you saw, even with my simple laptop, it was not terrible in terms of performance. And now I'm looking at some sample queries. Let's say I want to take a look at if we have something related to environmental awareness. First of all, good news is there is a bunch of relevant so of course there will be much more than that, because this is based on some kind of internal similarity, but these are the top results, and I think this is pretty satisfying, looking at, for example, some properties of the environment block which can be related to the actual issues of environmental awareness, which was my my search term basically. And also there are other things. Of course, this still should be verified if this is really as strong as it looks. But there's a fuel efficiency equation appearing here. And by this trace, for example, if I want to take a closer look at this guy, I get its ID from the modeling side, meaning that I can come back here and navigate for the environment, finding this block based on its identifier. And then there are also other queries, like for example, what properties do we store about fuel? And then, in fact, sometimes the word fuel appears, sometimes not, but then we get things which feel like being connected, relevantly connected to fuel storage, etc., etc. I could go on about this, but I think by now I have, or you have got the gist of it. So I will just return here for a quick takeaway to the end. So what we have seen is the system models have an inherent semantics coming from their graph structure and the encoded domain knowledge. However, they might be pretty hard to explore and comprehend due to their size and appearance. Therefore, we propose their textualization to combine the strengths of the MBSE and the NLU field of applications. That is, we want to reach a natural language model understanding here, and the first results which you have just seen are pretty promising. However, we are still at the beginning of a pretty long journey. While we have employed the state-of-the-art technology, which is BERT for context-sensitive language modeling, we still have to find a way to fine-tune it to perform even better in our role domain. And also, we might want to have a systematic evaluation to see if and how other BERT-like models really improve the contextual understanding of our system models. So with that, I end my talk. Thank you very much for listening. And if you want to reach out or have questions, I'm more than happy to answer. You can reach me on those channels which are listed on this slide.
Good afternoon, everyone. It's a pleasure for me to talk at Graph Data Science Conference 2021. I'm Dhanya. I'm working as a senior data scientist, and the topic today I would cover is graphs and financial networks. We all know there has been an increased attention towards stock market in general, and with the recent advancements in machine learning algorithms and deep learning algorithms, the focus is more towards the forecasting of stock price. Why so? Because these machine learning algorithms have uh, have shown improved accuracy or improved forecasting accuracy. However, we need to understand that the stock price is governed by various factors. One is the news or the financial news. Second is the market sentiment. Third, the interrelationship amongst various sectors or various industries constituting a particular sector. So before we proceed, first we need to understand an important concept related to the evolution of stock prices. So when we talk about the evolution of stock price, there are two schools of thought. First school of thought says that the stock price cannot be forecasted because the stock price movement is completely random, which is the random walk hypothesis. And the second school of thought says that the movement of stock price is not completely random, but it is governed by a set of common economic factors. So we take the second school of thought into consideration. So we want to see how the movement of stock price changes with respect to time, or how it changes dynamically with respect to time. So if it is governed by a common set of economic factors, so we should be able to get a cluster or group of stocks in as say we should be able to get a group of stocks. Hence, we started our work on financial networks. Uh, so the stock exchange we focused is the developed economy, which is the Toronto Stock Exchange, and we consider the S&P TSX Composite Index. So the TSX Composite Index consists of various stocks, and the number of stocks in the index changes every year. And we consider a period of 2 years from January 2015 until December 2017. And we took the constituent as on August 31st, 2018, which resulted in 245 stocks. And this represents the 70% of market capitalization. And based on the availability of the stock price throughout these 2 years, we had a total of 231 stocks for our analysis. So I just wanted to show the constituent with respect to the sector and how many stocks we had in each of these sectors. So this shows the constituents of the 231 stocks that we considered for our study. So now we come to the design or how we approach this particular problem. So the first one we wanted to obtain was the rolling correlation. So rolling correlation means it is a dynamic correlation that we get with respect to the time frame. So we have a moving window of say 21 days, 42 days, 63 days, 84, 126 and 251 days. So we used these time window for obtaining our rolling correlation. So why did we calculate the correlation? So the correlation tries to say whether the two stocks are moving in the same direction or whether it's moving in the opposite direction. Say for example, when we calculate this rolling correlation, if the value, so the value of the rolling correlation lies between -1 to +1. So when we say the rolling correlation value is 1, we say that two stock price are highly correlated, which means, say if the stock price of Facebook increases, then say the stock price of Microsoft also increases. So which means that these two stocks are highly correlated. And when we say that the correlation is 0, which means that two stocks are not at all correlated. And when we say these correlation value is -1, which means the two stocks are negatively correlated, which means if the stock price of, say, stock A increases and if we observe the stock price of B to decrease, then it is said to be negatively correlated. However, we are not using the rolling correlation directly in the analysis, because whenever we are trying to obtain any network or graph, we need a measure, we need a distance measure. The rolling correlation does not satisfy the criteria of being a distance measure. So we calculate a distance measure between, say, 2 points as 1 minus the rolling correlation square between those 2 points. And then we are trying to use the network. So when we talk about network, here we are using stocks as the nodes and the edges are the distance we calculated from the previous slide. So the distance based on the rolling correlation that we obtained. So when we talk about say correlation and network, so the immediate method or the most commonly used method for obtaining a graph based on correlation is the threshold correlation method. However, we are not going to use this particular method in our analysis. The reason being that we need to, as a researcher or as an analyst, we need to fix on the threshold above which we need to use the graph. Or say when we have, say, correlation between, say, -1 to +1, so we need to decide, okay, I'm going to use say the threshold of 0.5. So which in this case might result in many islands or many nodes as being as isolated. So instead of that, we are going to use two filtered approaches. So the first filtered approach is the minimum spanning tree. So minimum spanning tree is nothing but it's a subgraph containing connecting all nodes without forming a cycle. So this results in n-1 edges. The second graph that we use, or the second filtered approach that we use, is the planar maximally filtered graph. So this involves, so when we have edges, so edges here represents the distance. So here we are going to sort the edges based on the distances that we have in the ascending order, and then we are connecting the shortest edges subject to the constraint of planarity. So this results in 3 times n-2 edges. So from both the concepts of minimum spanning tree and planar maximally filtered graph, we can see that the minimum spanning tree is a subgraph of planar maximally filtered graph, and also we can see that planar maximally filtered graph retains maximum information compared to minimum spanning tree. So now we are going to see how these two approaches can be used to obtain the financial networks based on the economic conditions. So now when we talk about the graphs, so the next part is to obtain all the clusters or the groups. So in order to obtain these clusters, we use two types of measures. First is the centrality measure. Second is the peripherality measures. So degree centrality and betweenness centrality represent the centrality measures. The eigenvector centrality and eccentricity represent the peripherality measures. So we will discuss each of these measures in the subsequent slides and how they are used in the analysis. So first is the centrality, the first centrality measure that I am going to discuss is the degree centrality. So degree centrality represents the number of edges connected to a node. Say, so centrality represents the number of edges connected to a node. Degree centrality just represents the standardized measure that we are going to obtain. Say here, this is an example graph. So here we can say the degree centrality of say node 9 is 3 because it's connected by 3 edges, and say the degree centrality of 7 is 1 because it's connected only by one edge, and for node 8 it's 2 because it's connected by two edges. Now we come to the second centrality measure, which is the betweenness centrality. So this represents the number of shortest path that pass through a node between every between every possible pair of nodes. So here say A acts as a bridge, and here so here the betweenness centrality of node A would be higher compared to any other node in the graph, because whenever we are trying to connect say this particular node to this particular node, its shortest path has to pass through node A. So in which case the betweenness centrality of node A is higher. Now we come to the peripherality measures. So the first measure that we are going to see is the eigenvector centrality. So in case of degree centrality, we just looked at the number of edges connected to a particular node. So here we are going to say the quality of the nodes that is connected to a particular node. So if I have to put it in a very simple terms, we are not going to talk about the number of connections as a person I have. I am going to talk about the quality of connection that I have. Say for example, if I'm in an organization, I can say, okay, I know I'm like familiar with 10 people, but are any of those 10 people in say the highest position or in the position of say power where like they could help us in getting some approval or something like that. So if I have like even one connection who is capable of uh, helping us with some approval like in a short span of time, so that is more powerful than having that one powerful connection is better than having 10 connections who may not be so powerful. So that's eigenvector centrality. The last measure that we are going to see is the eccentricity. This represents the longest shortest path between a node and any other node in the vector. So based on the minimal spanning tree and the planar maximally filtered graph, so this is the graph or the network which we obtained for Toronto Stock Exchange. I know this is a little bit like cluttered and it's not like clearly visible, but I'll take you through the observations one by one. So I already told that we obtained these graphs with a rolling window of say 1 month, 2 months, 3 months, 6 months, and 1 year. And using the centrality measures and the peripherality measures, we were able to obtain central stocks or the core stocks and the peripheral stocks. So when we obtained the central stocks, we found the energy stocks or the financial stocks to be the core stocks or the central stocks based on the degree centrality and the eigenvalue, eccentricity, everything, like all four measures put together for both minimal spanning tree and the planar maximally filtered graph. And also we try to see whether the results are robust with respect to time and how similar are the stocks, the core stocks and the peripheral stocks that we obtained using minimal spanning tree and maximally a planar maximally filtered graph. So we were like, when we compared the stocks that we obtained for as a core stocks and the peripheral stocks, they were distinct with respect to time, which means that the core stocks remained as core stocks throughout different time windows, and the peripheral stocks remained peripheral throughout these time with respect to the different time windows. Also, when we try to check the similarity between MST and the planar maximally filtered graph, we were very confident that the stocks that we obtained as core were sort of like similar in both. So this represents with respect to the so with respect to the different time windows, say from 1 month to 1 year, the number of core stocks that we had common throughout the time with respect to say the minimal spanning tree and planar maximally filtered graph. So these are the number of stocks that remind us core stocks and that remind us peripheral stocks. Now coming to the major interpretation and how it is linked with the economic theory. So when we had this particular network, we try to analyze the network based on the four different measures. So we obtained, say, three major clusters. So the first cluster consists of financial stocks, consumer cyclical goods, and consumer defensive stocks. And the second cluster consists of communication services and technology. And third cluster consists of the energy sector. Uh, so when we look at the, so what are the implications from the economic theory? So the economic theory says that financial sector generally plays a major role in any economy. And this is the same results that we have obtained from the financial network analysis. So even here in case of the Toronto Stock Exchange stocks, financial stocks play a major role, followed by the consumer stocks. And also, given that Toronto is an say fintech hub, and there are so many financial organizations and institutions distributed here, it is they play a very major role. And also in case of say the technology, we do have an improvement in the technology over here, and that's also like contributing majorly to the stock index or the stock exchange. And third, the energy sector here plays a very major role. And finally, so I have already explained about the financial stocks among the core stocks. Now we how can we use this particular analysis, or how can we extend this analysis, say, in different ways? So the first one, in terms of how it can be helpful for investors or any portfolio management firms, that so we have considered say the financial network. We have obtained two clusters, two distinction. One is the core stocks, second is the peripheral stocks. So which means the peripheral stocks are kind of different from the stocks which we have from core stocks. So when we are trying to construct the portfolio, we can have say many of the peripheral stocks and some of the core stocks, but we need to still understand the distribution or the concentration that we want to focus on core stocks and peripheral stocks while forming the portfolio. Second, so here for the rolling time window, we had like used only 2 years of data for the analysis. It would be interesting to extend the analysis for a longer duration and also try to include, say, any major financial setback. Say, for example, 2008 financial crisis, or even last year pandemic, because pandemic affected many different stocks. So it would be interesting to understand how these networks changed with respect to say different situation. So the period in which I had done my analysis was kind of like quite stable, but when we have a major setback or major economic slowdown, how does it affect? And also, uh, the other important point is the stock price has a lot of uncertainty. We haven't considered the uncertainty when we calculated the rolling correlation. So it would be interesting to consider these uncertainty using, say, dynamic conditional correlation or using random matrix approach, and then see how these uh, networks would change. And thank you for your attention. And if you have any questions and if you would like to ask or if you would like to connect, you can connect with me on LinkedIn. Thank you.
Welcome everyone, my name is Milan, I'm a physicist and a network scientist. Before jumping into the middle of my talk today, let me just ask one very quick question from you. Have you ever experienced that unexpectedly bumping into an old friend or an old colleague or a mentor, or just getting to know someone new and interesting helped you to achieve one of your biggest success stories during your career? Well, so have I, and I believe that this is certainly a way networks work and affect our daily life and also our future success. So today I would like to walk you through a story where I show you how large-scale data and network science can actually be used to capture such details and methods and the working effects of networks in success. For this, I would like to show you three examples, three creative fields that are going to be our home laboratories today. These are music, film, and science. But before jumping into the science part, let me just give you a quick overview and give a few arguments and reasons why is it possible that in 2021 physicists seem to be dealing with questions that relate to social science and human behavior. So this actual whole field is nowadays called, for example, as computational social science, which means that there are researchers who have a background in more computation-heavy directions, for example, mathematics, physics, computer science, and also researchers who are coming from the humanities side with a background, for instance, in sociology or social psychology. And the main goal of these two different approaches is to use large-scale data and quant methods to understand different human behavioral patterns. These patterns can vary across a very wide range. For example, we can use data and behavior analytics to understand how our social media feeds reflect or correspond to our emotional state or even to our physical health. Moreover, we can even use these methods and data sources to understand how and why do, for example, pandemics spread all across the globe. Furthermore, we can even use data to understand how, when, and why does become one successful and what does one need to become successful in certain areas of life. To capture that, we will focus on the role of luck, randomness, and networks on three creative domains. These domains are going to be science today, film, where we will pick movie directors as a particular example, and music. In order to have a data-driven study, we will have to collect large-scale data, which we had from Web of Science that collects more than 1 million scientists. the Internet Movie Database that provides information about almost 1 million film directors and actors and producers and scriptwriters. And we also collected data from Discogs, which is a crowdsourced music discography website that collects all sorts of releases, masters, singles, and all kinds of collaborations from musicians all over the world. So after collecting these large-scale data, let's just take a look at it and have an understanding of how this data actually looks like, and what are the carriers, and what is the data representation that we can use to capture success. So first we had on the previous slide millions of individuals' career history downloaded into our database, and now let's take a look on how they actually look like. This example shows you the career trajectory of Steven Spielberg as a movie director. Of course, he had also been working as a producer, but now we focus only on the movies that he directed. And we put these movies into chronological order, one after the other. What this picture tells you that during the early part of his career, he didn't really have any big success. The popularity of his movies was really below the visibility threshold, let's put it that way. But after a while, after about 10, 15 movies, his movies started to get a lot more acknowledged and achieve much more success. Now, if there would be an online conference, then I would like to ask you to make a guess on what would be the biggest peak and when would it happen during his career. But now that we do not have this luxury, I will just spoil it to you to some extent and show that, all right, the biggest hit of the career of Spielberg came at like the second half of the career, somewhere around after 1/3 after the beginning. And I won't spoil the part that which movie was the one that peaked his career, but I will let you just Google it at home. However, the question that I would like to ask you and think about is that why would it be that, let's say, the 26th movie of Spielberg was the biggest hit during his career? So what did it happen? So first, probably he wasn't experienced enough, he didn't know enough, he didn't have enough courage to take on new and unexpected ideas. But later on, he just got all this experience together and managed to make the biggest movie of his life, right? So this kind of makes sense that you need some time. There is a certain learning curve on different fields, and after a while, someone makes it. So that's a very interesting hypothesis and certainly makes some sense. However, if we do not focus only on Spielberg, but we actually add the trajectory of thousands of other individuals, turns out that the yellow star, the biggest hit, occurs totally random throughout his career. So the big question comes then, why is it so, and how can we put this together in the context of networks? Because as you can imagine, and as we are at the Graph conference, movies are not the product of a single individual. So even if the trademark says it's a Spielberg movie, it was not just Spielberg, but many other people who helped him during the journey. So the question is, how can we capture, or how can we add the network aspect into this picture? And for that, let me just show you how we can build and how does actually the collaboration network of the top directors look like. Here we ranked the movie directors based on the popularity of their movies and only picked the top 2,000 and built their network. So there is a link between two directors if they have co-directed a movie, or even if they just co-occurred on the same cast. So it could be that one director occurred as a producer while the other one was actually a director on that movie, but there is still a connection between these two, as they are both directors, kind of playing the same field, and happen to work on the same movie as well. So this network graph shows us a few interesting things at first. For example, there is this very dense center, this core marked by bright blue, which means that there is the center, which is actually, not surprisingly, Hollywood, and all the biggest shots are right there. However, there are a few more clusters, a few more communities in this network, like the red one on the right, which is, if I'm correct, the cluster that corresponds to European movies, while the gray one on the left, on the opposite, is actually about the Disney movies and all these animated cartoons and things that are less for adults but more for kids. So nevertheless, we can see that there is an interesting and very peculiar network structure behind the movie directors' collaborations. And now let's put it together with the impact evolution. So the impact evolution tells us that from year to year, from movie to movie, the current success of a director changes. And the reason behind it that the different movies perform differently. And underneath what we can see is that there is actually a network evolving, because at every movie we will have a network similar to this one, just with a few slightly small changes across the network structure. So one movie occurs, then there is a certain structure. Next year, a new movie occurs, or thousands of new movies occur that reorganizes and rewires the network a little bit. And then new year, new movie, new year, new movie, which if we project onto the level of the individual, we will see that first, for example, Spielberg was this small peripheral node marked by blue, but after a few movies or after 20 movies, he suddenly became the center of his own network. But after a few movies later, he started to slowly drift out of the center of that network. We can also capture this in a very quantitative way, for example, by using network centrality measures like page rank centrality, betweenness centrality, or closeness centrality. And turns out that it doesn't really matter which centrality measures we pick. The network position seems to have a very similar rise and fall arc like the one his impact carrier shows. So this figure really tells us that it seems that in the case of Spielberg, impact and network evolves hand in hand. So does it mean that network and impact are the same? So we can just have another measure besides, for example, box office revenue that captures success, which is networks, or there is something more to it? To figure this out, we stepped away a little bit from our beloved Spielberg and added a few more thousand individuals that had significantly long trajectories so that we can do all the network analytics. And we carried out this same comparison between the arc of the network and the arc of the impact. And once we do this, surprising results we have found are the following. So it turns out that the patterns corresponding to Spielberg are actually just a very small minority of the whole population. Only 12% of the individuals show the same pattern. However, it turns out that there are two major and complementary behavioral patterns. For the first one, a great example is the French DJ and producer David Guetta. In the case of Guetta, turns out that first he had been out there for a while, had some quite decent hits. However, his network was not really up in the skies, while after a while his network suddenly peaked, and once this peak happened, shortly followed the biggest hit of his career as well. So it seems that in the case of Guetta and the people like Guetta, network peaks first, and the biggest hit only follows afterwards. However, the complementary behavior seems to exist as well, for which a very lovely example is the director of Star Wars, George Lucas. Turns out that Lucas had been working quite in great silence without any major recognition for quite a long period. And then all of a sudden he came up with this brilliant idea of Star Wars that basically skyrocketed his success right up and helped him to be one of the biggest directors ever. And shortly after his biggest success, his network also peaked. So history kind of tells us that first he had been a lone wolf working all on his own in the basement, but afterwards he managed to make the biggest hit. He became also central and got many new friends. So the question now is that, is it better to have a network first or success first? So should you be a networker person who gets the right connections, get the right resources, get the right people around him or her? Or it's fine, or it's better to be a lone wolf, a brilliant guy, or who is just sitting on his own and working something out and getting all the credits afterwards? Well, good news is that it turns out that it doesn't make a big difference. First of all, it turned out that we cannot predict which of these two categories someone's career is going to fall into if we only consider biographical information, for example, the birth location or birth country of the directors, or if we consider any career descriptors, for example, the number of movies or the number of releases someone had. So it seems that it happens pretty much random, so you don't really have a choice whether you want to go a networker or a non-networker. But what is good news here is that it turns out that there is no major difference between the expected success of the two groups. So either way, if you are doing well, you can achieve your right spot also with your networks, but also with your skills. And after having this broader overview of directors and mathematicians and pop musicians, let me show you a very specific example that actually came out as a fun project first and then ended up being published in scientific reports, which is about DJs and mentorship in electronic music. So the framing that you need to get here first is that every year since the late 90s, the British DJ magazine has been organizing this top 100 DJs list, which is basically a ranking based on popularity. So all the fans of electronic music have the chance to go online, go up to the website of the DJ mag and vote for their favorite DJs. The result of that vote is that millions of people vote for their favorite DJs each year, and that way DJ Mag curates the top 100 list of that year's most popular musicians. This has been a list for about 20 years, and roughly 600 DJs have been there already. However, if we take a closer look and also use some data analytics, turns out that there is a very thin layer at the top, roughly about the top 20 of the DJs, who have been kind of the stable all-time classics. So there is a very small fluctuation, drastically smaller fluctuation in the names in the top 20, like than it is in the bottom 80. So it turns out that there is a small elite at the top of the DJ world. For example, Armin from Buren, Tiesto, or our very familiar friend David Guetta have been there for a while, and it seems that this top is kind of logged in. And the question is that why is this top logged in? How can we explain that? And first, it turned out that it's not purely driven by popularity and, for example, the play counts they collect in music providing services. So we decided to dive into the network aspects. To have an understanding of the network structure behind these DJs, we needed to collect their release information to know that which DJs released together songs, which year, and how often, and what was their success. After building this network, we arrived to the one that you are currently seeing on the slide, which has 540 nodes. These are all the DJs. The size of the nodes is proportional to the best rank of the DJs. So the larger the node, the more successful the DJs were. So you can see that there are a few bigger nodes like David Guetta or Carl Cox. They have actually been the #1 DJs of the world at some point during the past 20 years. After building the network, we also captured the communities in this network, which you can see in the coloring. Turned out that there are 7 distinct communities in the network. And what's even more interesting is that all these communities are driven by these stars, meaning that all of them have 1 or 2 big stars who have ever been #1 DJs of the world. And also turned out that these biggest stars were one of the earliest members of these communities. So it seems that once these big stars occur in this network, and they basically start to grow their own network, their own success, and the community around themselves as well. So it looks like there's an effect of building networks, and that's what these top DJs are doing. And the question is that whether this is intentional or whether we can pinpoint this at a more granular level. And our hypothesis here was mostly inspired by social science research that there should be an effect or a phenomenon called mentorship involved. And we have a good reason to believe that this is the case, also based on case studies and also knowing that some of the biggest stars have their own record labels, and this way they are also collecting all the new people around them. For that, we define mentorship as follows. So we have a DJ who have been in the top 100 already, and someone who hasn't been there yet. By the next year, they collaborate, and the year after, the second DJ occurs in the top 100 as well, which makes them a mentor-mentee pair. Of course, this is not necessarily the best definition or the most accurate definition. However, we tested a couple of different definitions which are kind of similar to this one, and they are detailed in our paper as well. And it turned out that there isn't really a big difference on how exactly we define mentorship. the results are all the same. Turns out that half of the DJs in the top 100 arrived there based on their mentors, so they have the right mentor that helps them to get into the network. And turns out that 30% of the DJs, so more than half of the mentored ones, have only been mentored by this very small layer, this very small elite on the top. So it turns out that if you are mentored, then you are most likely to be mentored by one of the biggest stars. And is this good for you? Is this mentorship helping you in any ways? Well, turns out it certainly does. To capture that, please take a look at this graph where we show the best rank of the DJs. So the closer to 1, the better they are. And we split them into two groups. One group is marked by red. They are the ones who haven't been mentored, who just arrived to the top 100 on their own. While the blue ones, the blue line corresponds to those DJs who have been mentored. Well, if you have been reading graphs lately, you can quickly tell that there is a huge difference. Basically, the trends are inverted. It seems that those who had been mentored before are always in the upper half of the ranking, while those who haven't been mentored are typically in the bottom half of the ranking. So there is kind of an inverse trend. So if you are mentored, you have much bigger chances of getting a nice spot in the ranking. However, there is also a downside of this mentoring, which you can see in this graph. So if we control for the best rank of the mentor, so the star mentors are there on the right of the graph, under 20, turns out that the mentees they have, even the best mentees, statistically speaking, never achieve the same success their mentors had. So it turns out that being mentored helps on average. However, if you have a star mentor, then it's basically sure that you won't be such a star yourself. And just to wrap up very quickly, so it turns out that success can come at any time, but networks certainly help. So if you have the right network, that can boost your success right there. And if we focus on a very particular segment of networks and success, mentorship, turns out that gatekeeping exists in electronic music, and we have good reasons to believe that this is the same in other creative professions as well, where the network can help you to get successful. However, it's not enough to arrive to the top.
Hi everyone, thanks for having me. My name is Trey Grainger, and today I'm going to be talking with you about interpreting intent with semantic knowledge graphs. Just a little bit about me. I am the founder of SearchKernel, the AI-powered search consultancy company, and I'm also the CTO at Presearch, the decentralized web search engine. Additionally, I am the author of the book Solr in Action, as well as AI-powered search. And most of the code examples I'm going to go through today to teach you about and show off what you can do with semantic knowledge graphs actually come from chapter 5 of the book. So if you're excited about this topic or interested in learning more, definitely check it out. So to get started, let's just talk about a knowledge graph in general. So, a graph is composed of nodes and edges, and a knowledge graph is a graph that essentially models a domain and the information available within it so that you can check with the graph and traverse it and learn and reason about information within your domain. It can be very useful in my field, which is building search engines, to be able to understand user queries, for example. However, building a graph is at any large scale is a very expensive process, and those graphs can be hard to maintain. So we like to automate as much of that process as possible. One of the ways to automate the generation of graphs is to use open information extraction, which is the idea of extracting arbitrary nodes and edges using things like parts of speech, where we take some incoming text, like for example, data scientists build machine learning models. They also write code. We parse that out grammatically to understand the subjects, the objects, and the verbs within a sentence. And then from that, we can learn facts like data scientists build machine learning models and data scientists write code from they also write code and data scientists in the original text that came in. So using this technique, we can extract out information to put into a knowledge graph explicitly from our data, using a natural language processing library. Another way to pull out information is to use common linguistic patterns. So for example, there's a type of pattern known as Hurst patterns, which allow you to extract out hypernym, hyponym relationships or ISA relationships. So given certain types of linguistic structures, I can, for example, pull out that, from up here, that machine learning is a skill, Python is a skill, commute time as a job benefit, those kinds of things by just parsing the text coming in. And ultimately, these can all get mapped in. Microsoft is a tech company. San Francisco is a big city. These could get mapped into this giant graph of essentially taxonomical relationships of sort of hierarchies of what types of things are other types of things. However, there's another kind of knowledge graph, which is the one I'm going to be talking about today, called a semantic knowledge graph. And in this type of knowledge graph, we actually take the text itself and the relationships within the text as the graph and traverse it to find semantically related terms, phrases, categories, etc. So the way a semantic knowledge graph works is very similar to the way we would think of relationships in a structured database. So in a database, we would have discrete values, different kinds of values, but ultimately we have values in fields that can be keys to values in other tables. And so in this case, I can join on a foreign key and understand that the context from the first table applies to the data in the second table for that particular row. When we're dealing with unstructured data, however, this becomes a little bit more challenging because we don't have clear columns and rows, we just have chunks of text. However, if you look at the text actually has significant structure to it. It's just linguistic structure and it's, the reuse of terms across multiple documents. But within text, we've got, character sequences that ultimately build up, like ENG, engineer, these all build up to larger terms like engineer, engineers, engineering, which build up to phrases, which ultimately get added to documents and sentences. And so if we can harness these relationships in the semantic structure of our text, we can do some very interesting things. So taking that same text that you saw a slide ago that was just a blob of text or unstructured information, we can actually use the individual words and terms within that text and any other unstructured information like videos or images or audio, and we can actually relate it together. So in this case, you see my name, Trey Grainger, he, his, my name sort of extracted out of this video. Those are all essentially keys or entities that can be joined across these different data sets, in this case, documents. There's also, a name of a conference here, dates, names of companies. These things all, if they exist in multiple different documents, if we can relate them together or join them across those documents, we can pull context from one document into another document and look at that context across our entire corpus of all of our documents. The way a semantic knowledge graph works, or the way it's structured, essentially relies on two different data structures. One is an inverted index, which is a mapping of all of the terms in your document, in your documents to the IDs of the documents in which they appear. And then what's called a forward index, which is the opposite. It maps all document IDs to a list of all the terms that appear within those documents. So this essentially allows us to start with any term, any keyword, or any combination of keywords, look those up, get a set of documents, and then start with any set of documents and then look up all the terms. By having both of these, going from any term to any document or going from any document to any list of terms, we can actually traverse like a graph through our text. So in this case, I have a skill of Java. So this is the term Java in a field called skill in our document. I can look up all the documents that contain this term of Java. And then from those documents, I can go look up all the other skills that exist within those documents or terms within the skills field. So in my field of work, this is a search engine that has this inverted index and this forward index. though this could be implemented outside of a search engine. But a search engine would be the natural type of structure in which you would typically find an inverted index. And if you're familiar with any open source search engines, Apache Lucene, Apache Solr, Elasticsearch, Vespa, any of these search engines have an inverted index and usually a forward index built into them naturally. So if I can go from a term to a set of documents to another term, then there's no reason I can't go multiple levels deep. So in this case, what I'm doing is I'm starting with the term of Java, finding all the documents related to Java that contain Java, looking for other skills that might be in those documents, finding other documents containing those other skills, and ultimately traversing to a job title. And so I can go as many levels deep in this traversal as I want, but ultimately this structure allows me to traverse from terms to other terms and from those terms to titles, for example. So just to show you some examples of what we can do with the semantic knowledge graph once we have it built, which is as simple as indexing documents into an open source search engine like Apache Solr, which is what my examples are based upon. What I'm going to do is I'm going to index some data sets here. They're Stack Exchange data sets from postings on the Stack Exchange forums. And specifically, I'm indexing the health data set, cooking, sci-fi, outdoors, travel, and DevOps. So once I've indexed those data sets, the first thing I'm going to do is just query the semantic knowledge graph for the term Advil, querying the health data set. And I'm just going to say, return me back the top terms that are the most semantically related to the term Advil. And out of all of the terms, out of every keyword in any of our documents, what the semantic knowledge graph does is it traverses and it finds that Advil, Motrin, Aleve, ibuprofen, another spelling of Aleve, Tylenol, naproxen, and acetaminophen are the most semantically related terms to Advil. And that's actually a nice ranked good list of highly salient terms associated with Advil. I can do the same process with another query. In this case, I'm searching for vibranium. If you don't know what that is, it's a very, very strong and powerful metal, imaginary, made up in the Marvel comics, specifically associated with the Black Panther character, for many of you who have seen that movie. But what I find is that when I search for vibranium, that the terms most closely associated with vibranium are Wakanda, adamantium, and then Black Panther and people from the Black Panther movie. Interestingly, Wakanda is where vibranium comes from, the country, and adamantium is another kind of very strong metal found in the Marvel comics. So still, the semantic knowledge graph is essentially helping us find other very conceptually related terms associated with what we started with, which was vibranium in this case. From those terms, we can then do very interesting things. So in a search engine scenario where I'm trying to interpret the intent of the user, instead of searching for just the text of vibranium across all my documents, what I can actually do is take those terms and use them to expand the query. So instead of running a query for vibranium, I can run a query for vibranium or Wakanda or adamantium or panther or sort of any of these highly related terms and bring back more conceptually driven search results as opposed to just text-driven search results. Another thing I can do, so I showed starting with a query, but you can actually start with an entire document. So in this case, I just made up a fake document here. It just says this doc contains the words Luke, Magneto, Cyclops, Darth Vader, Princess Leia, Wolverine, etc., and a bunch of other words. And I'm going to say that, given that this document is supposed to be about Star Wars, what I want to do is score all of the terms in this document based upon how related they are to Star Wars. And what I actually get back is Luke, Darth Vader, Force, Galaxy, Blaster, Princess Leia. All of the Star Wars related terms scored high in this results list, and then all the other terms scored lower because they are either not associated or have a negative association with Star Wars. And so from there, I can actually take my original document, rank all the terms in it based upon how well they describe the document, and then set some threshold. In this case, I'm going to take anything that scores higher than 0.25, and I'm going to use it to generate one of those expanded queries like we saw in the last example. So in this case, I generate a query of Luke, Darth Vader, Force, Galaxy, Blaster, and Princess Leia with associated relevance weights. I can pass that to the search engine, and then once I've done that, I actually now see results coming back from the search engine for things like, was Darth Vader at his strongest during episode 3? Or why couldn't Snoke or Kylo Ren trace Luke using the Force? Notice none of these have the term Star Wars in them, but they're conceptually related to my original document, and they match based upon the search. So what I've done is I've built a content-based recommendation engine that can start with a document, figure out what's the most important in that document, and then find other documents that are similar. Another thing I can do with the semantic knowledge graph is explore arbitrary relationships. So in this case, this is another superhero reference. Sorry if that's not your domain. I'm going to search for Jean Grey from the Marvel Comics, and I want to figure out who she's in love with or who is in love with her. So what I'm going to do is search for Jean Grey, traverse through in love. I'm sort of creating an edge on the fly just based upon that text. And then I'm going to find any terms that are related to Jean Grey through the relationship of in love with. And what I actually get back are Jean and Grey, which, she's obviously going to be in any content related to herself being in love. And then I get Cyclops, Summers, Xavier, and Wolverine. And so if you're familiar with the Marvel Comics, you would expect Cyclops and Wolverine to come back because those were two of Jean Grey's love interests. But Xavier might feel a little strange. Turns out that actually Professor Xavier had a thing for Jean Grey. Not a lot of people know that, but it is talked about in the Stack Exchange forums. Therefore, the semantic knowledge graph is able to bubble up that information, even though it's not necessarily common knowledge. And what we've essentially done here is we've started with a note of Jean Grey, found in love with that semantic phrase, and we've traversed through from Jean Grey through in love with to go find these other terms that are pretty much the exact answer we wanted to our question. Again, we've started with just text. These are just single individual keywords. We could run some natural language processing on them to generate phrases or what have you, but we've done no modeling of this data. This is purely text and traversing through the text in our content. Another thing we can do with the semantic knowledge graph is we can classify content, classify queries coming in from users. So for example, if somebody searches for Docker, we can classify them automatically to the DevOps category by traversing from the term Docker to the category field and then finding the top categories. So in this case, Docker gets classified to DevOps, airplane to travel. Interestingly, if I search for airplane and crash as a query, instead of travel, I get sci-fi, because it's much more likely that you'll be dealing with sci-fi content if you're talking about an airplane crashing, because in the real world, airplanes don't actually crash that often, thankfully. Alien maps to sci-fi, etc. And then this one's interesting. If I search for driver, it returns back two categories, travel or DevOps. So if I modify it to be driver and taxi, it gives me the travel category. If I modify it to be driver and install, then it becomes the DevOps category. But interestingly, because this isn't just a classifier, this is a graph, I can actually, after I've traversed to the top category, I can then traverse to find other related terms within that category. So this is a really good way to be able to disambiguate multiple meanings of terms. So for example, if I search for the word server, then it brings me back the DevOps category. And within that category, server means things like Docker, deploy, and SSH. Versus if I look in the travel category, then server means things like tipping or tip, which would be for like a food service worker, or somebody working in a restaurant. But you also see VPN, which is a kind of server that if you're traveling, you would be particularly likely to be using. And so this is not just generating a list of related terms, but it's able to generate them in a very contextual and nuanced way based upon the exact terms typed in the query and the categories and fields within to which you traverse. Drivers, another example here, if I look for driver for in the context of travel, I'm seeing things like driver, driver's license, car, etc. If I look for driver within the context of DevOps, I get things like IPAM, overlay FS, things like network drivers and hardware drivers. So again, a very contextual list of related terms based upon the underlying category, with that category being based upon the context of the query. And so why does this matter? If I think about interpreting intent with semantic knowledge graphs, if you're building a search engine or interacting with user queries in any way and you need to interpret and understand them, it allows you to do things like taking this query of top barbecue in Berlin, understanding that Berlin is a location, top is describing some characteristic about the next word barbecue, and that barbecue actually is most closely associated with restaurants, and within that category means things like ribs and brisket. Versus if somebody were to type in barbecue grill, I can take the nuance associated with those words and understand that grill is actually more closely associated with outdoor appliance. That's the category in which it's found. And within that category, barbecue now takes on a different meaning, which is grill, propane, or charcoal, as opposed to ribs and brisket. So this is a great example of how you can use semantic knowledge graphs to interpret the intent of your users. And that's my time. So with that, I say thank you. And if you have any questions about semantic knowledge graphs or how you might use them or building intelligent search engines, please check out my book, AI Powered Search, or reach out to me at Trey at searchkernel.com. Thanks so much.
Hello, my name is Mihaly Minko, and I work at Milán Applied Arts University. I'm the member of the Immersive Media Research Group, and together with Ágoston, we developed two installations to the exhibition of Albert László Barabási that was open last October. I would like to present basically our findings to you in order to show how network visualization can be extended, how the boundaries of these types of visualization can be extended and enhanced and approached in a different way. Basically, if you think of any type of visualization, the most common things that come to one's mind are those on the surface, on the 2D screen, or on printed materials, or posters, or basically anything that is on the two-dimension coordinate system. What we wanted to basically experiment with was that how can we add more layers to these, how can we overcome the boundaries of two dimensions, and not by using any 3D software or computer screen that is able to show us CGI, 3D or whatever, but to change the perspective some way and show these beautiful networks from a different viewpoint. What you can see on the screen are two different visualizations. On the left-hand side, basically, you can see a visualization made in processing that shows the rhythmic changes of poems during the 17th century. And on the right-hand side, you can see a network visualization. These are both visible properly on a 2D screen, and they both have their own restrictions and frames that they fit into. They use visual variables such as color, size, or width, and also position that basically are well-known visual features of data visualizations. But these are quite common. These are quite well-known, and for us researchers, it was interesting to figure out if there is any way to extend this, to change, as I said before, the viewpoint. The first step was a collaboration agreement between our university and the Barabashi lab, and so we could gain access to their data, and we could use it to represent the networks in ways we didn't really dreamed before. The first project that we worked on together was the Foodome network, a network sculpture, a 3D printed food ingredient network that is a famous research area of the lab, which shows basically connections between recipe ingredients via compounds found in those ingredients, so chemical compounds. So, for example, if you put two fishes next to each other, they will smell quite the same, they will look quite the same, and the taste will be, yeah, quite the same. That's because they share quite a lot of compounds regarding taste, their smell, and their color, and their etc. etc. Lots of different but shared compounds, and this connects them, and this connection is what was 3D printed in the network sculpture. We got printed network from the lab, so we could set up a workshop where participants were playing basically the ideas of augmenting networks and augmented reality and network sculptures, physical visualizations or physicalizations, and they pretty much enjoyed it. And we also gained some insights how one approaches these problems, or what could be good solutions for these issues. The method was pretty straightforward, usual data collection, data preparation, and data representation steps. We got the data from the lab, we changed the data a little bit in order to fit into the system that Ágoston and Brigitta were developing. So we worked together with Csaba, both from the lab, on this, and basically squeeze the data into a shape that we wanted to use for this project, and then try to represent it in augmented reality. The representation was attached to reality, and therefore we needed to use the actual physical sculpture and fit the model that we built in 3D onto it. And this was quite an interesting thing, because as you can see here, there are quite a lot of nodes, quite a lot of connections, and this is an actual network, as I mentioned, and this is the Foodome network. You can see the fishes, you can see the meats and the wines and the cheese and the fruits, etc., etc. So different food types on the screen, and we were adding it to the actual physical sculpture, which looks like this. This is a 3D model of the physical sculpture, but the 3D printed sculpture looks exactly like this. So there are nodes in the actual physical reality that are connected to our augmented reality application, and therefore we can add an extra layer of information via network visualization to this physical sculpture, which is really interesting. So let's see a short video. How does it look, and what are those key points that I wanted to show you. So this is the sculpture. There are different groups that share the same compound. So basically we needed to show that these belong to the same group, these nodes belong to the same group, and even they share the same chemical compound, like the same taste, the same smell, the same color, look, etc., etc. So we created a 3D representation of the actual physical sculpture and fit onto the 3D printed network sculpture. As you can see, we can scale the model, we can rotate, we can dim the environment to show just the model. We can step closer, and as you can see, there are different zones, which is kind of important, because in different zones we can show different groupings or aggregations of information. If we are really close, then we can show node level information. If we are a little further away, we can show groups. In this case, this is the overview screen or distance, where we only see some visual sign. But if we step closer, then the groups become visible, and we can select different groups. We can click on them and see what are those, in this case fruits or dairy, what are those, and through which connections can we go to dairies to alcoholic beverage, for example. And yeah, this is the node before the node view. This is the cluster view, and if we step a little closer, then we can see the actual nodes, and we can select individual nodes, and we can see some more information, more detailed information on the nodes, like how many recipes have it, how many compounds does it have, or how many countries do they use that recipe. There are sound-based notifications between the changes of the different zones, so therefore the user will hear that she or he actually stepped into or out of a zone to another one, and we provide a message if the user steps too close to the actual sculpture, that yeah, maybe better to step back. And if you are too far away, then you don't really see well, not much, because you are just too far away. So this is how it looks. So this is the augmented reality sculpture, network sculpture, and these are the tools we used, and basically this is the crew. It was really interesting because this required quite different expertise on different things, but yeah, it was fun and a rewarding experience, and we hope that you check it out at TKM next, maybe in April. So the second one was the Hungarian Artists Network. This is a little bit simpler than the previous one, because we use a drawing robot, a pre-built piece of hardware that is able to draw onto surfaces with a pen. The interesting thing is that we used, so this is an actual pen and actual paper, and the robot draws basically whatever you put into it in an SVG form. And we got data from the lab, the Barabashi lab, and we used that to visualize Hungarian artist network throughout the same steps. And basically, in this case, we added some more information on the number of exhibition of that specific artist. So whenever she or he was born, how many solo exhibitions did she or he had in the past, and what were the top 3 most important galleries or museums or exhibition places in that specific context in which he or she worked. So these are some tryouts, some examples, some experiments that we made with or without labels, with different densities of artist networks, and we decided to put these onto 50 by 50 centimeters black sheets of paper, and onto a white wall. So around 100 artists would fit onto the available space in the museum. And you can see on the left side of the screen the drawing robot. And basically, Agoston built a piece of code, software that processes these SVGs and instructs the robot to draw it. Each day it draws one network, and the colleagues at the museum, they put it onto a specific place, and the users can see the robot drawing during the day, and also how these small sheets of paper fill in the wall day by day, how basically this living thing just grows on the wall. So this is the drawing robot, and these are so we try to work around the width of the edges, because those can exhibit important information. But in this case, we decided to not to go on with that, because the drawing robot is not able to draw different widths or with different pens during the day. It can only use one specific width. So we needed to show something else, and therefore what you can see as the size of the nodes is the prestige of that specific exhibition place where the artist exhibited her or his work during his active years. And this is how the robot looks when it works. Quite meditative way of doing things. I would say we really like to watch it when it draws these circles and lines and small letters onto the paper. It's really like meditating with it. So, and it's kind of beautiful, I think, and I hope you agree. Let's just watch it for a while, because it's nice. Well, thank you for your attention. I hope you found these two projects interesting. And if you would like to reach out to us with any questions or comments, or just work together on something, you can find us on those email addresses. So let's get in touch.
Hello, I'm Luis. I'm very happy to be here to talk about networks, graphs, and network science applied to cities and how we can use these tools to analyze and improve the quality of life and different aspects of our cities. So, first, a little bit of my background. I'm an architect by training, and I have been working around cities since 10 years ago or more. And I'm also very interested in public policy and how can we analyze and how can we use network science tools to work in the intersection of these three different areas. So what I'm going to present is part of my PhD research, and it's how we have been using this the network science foundations to analyze and better understand the cities. So the first project that I'm going to talk, it has to do on how can we develop some bicycle algorithms to improve the accessibility of bicycles in cities. And for this one, and as for all of the projects that I'm going to talk, we're taking the city as a network. So we're taking every intersection in the city, we map it as if it's a node, and then we start building this network with the different links connecting intersections. So take, for example, this city, and we start adding first the nodes in each one of these intersections. Then we add the links between intersections every time we have a street or every time we have some sidewalks. And then at the end, we ended up with one network that we can start analyzing. And of course, we can explore this and we can extend this framework to build some multi-layer networks. In this case, this is Manhattan, and it's a representation of the different layers in the transportation system. So we have the pedestrian infrastructure, the bicycle infrastructure, all the subway, and then the streets. So we can start analyzing each one of these layers separately or together. So I'm going to show you what are we doing with this. For the first one, we have some measures, of course, we can take for each one of the layers. And then in the first project, we start analyzing just the bicycle layer. And what we realized after comparing multiple cities was that most of the cities in the different layers, they are consolidated in just one giant component. So this means that we can start walking around the city without having to move between layers, and we can access different areas in the city. However, if we just analyze the bicycle layer, we found out that it's quite fragmented. So take, for example, the case in London, that we found that even though they have a very good bicycle infrastructure, it's fragmented, and they have more than 3,000 different components. So 3,000 different small separated small networks inside this layer. And the same thing happens in even super bicycle friendly cities like Copenhagen, where they have around 100 different components. So this means that they have one that it's quite big, but then they have some areas in the city that are not connected. So of course we check if this is something that it's actually happening, or if it was just something on the data. And this is the case in Budapest. And we found that yes, there are some places that we have some bike lanes, and then at some point the bike lanes just disappear, or they come into the sidewalks. So with this in mind, we decided how can we start using the graph and the network science tools to propose some algorithms to improve the connectivity. So we developed two base algorithms. So we have the largest to closest component. This one is doing, it's taking the largest connected component, so the largest graph in the system, and then looking for which one is the closest and connect it. Then, and so on. Then we have the largest to second algorithm, and this one looks for the two largest components and then start connecting them. And we have two baselines to measure, to compare our algorithms with. So we have the closest one, that it's we look for which one of the components are closest between them, and then we start connecting them, like it's a minimum investment approach. And we also have the random to closest component. So in this one, we randomly pick one component and we connect it to the one that is closest to it. So with these four algorithms, we analyze 15 different cities in the world, and this is an example of how the algorithm is working in Budapest. And we start seeing how, after connecting different components and just investing as little as 10 kilometers, 10 new kilometers or 5 kilometers into the system, and 5 new kilometers in this network, then the fraction of all the kilometers that are bikeable in the city dramatically improves. So we measured this for all the algorithms in all the cities, so for each one of for the 4 ones in the 15 different cities, and we found that all the cities are improvable, and that for all the cities we can start adding as little as 5 kilometers and see huge improvements. So take the case, for example, in Portland, that we can add 5 kilometers and move from having a little bit less than 50% of their the whole length of kilometers inside one component to move to almost 100% of the existing kilometers connected in just one giant component. And then, of course, for some cities, we have to invest a little bit more. And for most of the cities that we analyze, if we just invest 35 new kilometers, we can move most of them above 75 to almost 85% of being connected. The same happens when we measure for directness, and directness is a measure that we use to compare the two different layers. So the idea behind directness is how faster it is to move from point A to point B using a car, like how direct can we move using a car versus how direct can we move using a bicycle. And we can see that the bicycle is losing a little bit, or in some cases a lot, and then after we start investing, the directness improves significantly. So this means that we can provide new ways to commute from point A to point B, being as close as if it's just using the street layer, or commuting by car. Then the second project that I want to present today, it has to do with how do we measure the quality of life in cities. And this is a project that it actually started as an idea, as a consultancy, because we were doing some work with some friends for the municipality in Budapest, and they asked us to tackle the question, how can we measure the quality of life in the city, and how can we improve it? So we came with this idea to complement the city using the graph, and then reading and thinking, we completely agree with this quote from Jane Jacobs. So the life in a city happens in the sidewalks. So this is an interesting project because, as I told you, we were working with stakeholders, with public policy experts, with politicians, and then the last goal was to build some public policy using some data methods. So for this one, we start with the pedestrian network of Budapest. Then we have different points of interest that we also projected into the network. So we had some data about shops, parks, family-friendly amenities and so on. And we also had some data about different city attributes like air pollution, crime rates, and population living into different neighborhoods of the city. So what we did was we provided a method to compute the quality of life based on accessibility to services and weighted by the safety and the environment. And the interesting part was that we were able to measure the quality based on the nodes. So the main idea behind it is how easily can someone from any part in the city access different amenities in the city, and how are those amenities connected, how safe is that area, and how good or bad the environment in the area is. So when we combine all of this, we have a measure to test the quality of life quality in each one of the nodes in the city, so in each one of the intersections. So our amenity index, what was computing, it's how important it's the amenity. So working with experts into different areas, they were saying us like, okay, what's the importance or the relative importance that they are assigning to each one of the amenities. So is it more important to have a park, or is it more important to have, I don't know, a coffee shop in one area? So of course it's a very subjective thing, but people working in the city, they have some ideas about that. So we wanted to incorporate that knowledge into the method. And how many people does the amenity is being shared with? So we have the population data, and we assign the population to the nodes. And then with the population, the nodes, we were able to capture like how many people live around each one of the amenities, walking by 5 minutes and so on. So we can somehow imagine the level of service that they provide, and how long does it take to reach the amenity. So we can calculate using the network, looking for shortest paths, what's the easiest way, and how long does it take to calculate from any given node in the city to any of the amenities. So we built this, we use an approach to calculate some border noise based on the network. So we start for each one of the amenities, we categorize them, and for example, in this one we had family support with kindergartens, parks, and playgrounds. So we take just parks in this case, in this example, and we start calculating the areas of services, and then we had which one was the closest park to each one of the nodes in the city. We did the same for all the different amenities and all the different points of interest, and at the end, measuring this accessibility index and measuring the quality, the pollution, the safety, and so on, we were able to provide a life quality index in a very granular way. So we have the index for the whole city, and we can see that some areas in the city center, they have the highest quality, the highest life quality, while some areas in the outskirts of the city, they are in the lower spectrum. And then, having all of this in a granular way, it is possible to start aggregating them. So we can aggregate, and as we show in this one, we have it for the different districts and also by the different categories that we were analyzing. So it is interesting to notice, like for the family support, that or family education, that it has to be by law a school in each one of the districts. We can see how in some areas of the city they have better access to education facilities than in some other areas of the city. So these methods at the end help to provide some data-driven decision making into the city. Like if the mayor has to invest, or they have to start investing at some place, something they can look at what's missing in that part of the city. Then we compare our results, or what we found, using the networks behind the city to analyze the real estate prices, and we found some pretty interesting correlations, like the higher the life quality index is, then the higher the price per square meter. And also, same with culture. With the environment, it's a negative one. It has to do because the environment we were measuring with how polluted it is. So as the higher polluted, then the lower the price, and the less polluted, the higher the price. And yeah, it has been used now to start thinking about how the city can be improved. And lastly, this is a new project that we have been working on. It has to do with how can we take understand the urban form, and how the urban form has to do or correlate with accessibility to different amenities. And this is quite important in these times that we're doing everything online and we're in lockdowns and so on, because then in this project we are measuring the accessibility to food shops, hospitals, and pharmacies. So in this one, okay, yeah. So take for example these different areas in the city that are actually in the same neighborhood, and we have some places that they have these huge city blocks. Then they are not quite permeable. It's not so easy to walk around there. Then we have these summers that are a little bit more fragmented, so it's more easy to walk around the different areas in that neighborhood. And then we have some other close, gated urbanizations with some cul-de-sac and so on, that it's, even though they look a little bit more permeable, they still, if we want to move from one place to another, we have to do like these long walks. So we start measuring with that the accessibility for pharmacies. This is the case in Guadalajara, Mexico, and we can see how different areas in the city have better accessibility and which areas in the city have lower accessibility. So in the middle of the COVID pandemic, it was or it is a first necessity to provide these kind of tools and to understand how people can freely move around the city and access different medications, food, hospitals, and so on, and how easy it is for them to access. So this is a work in progress right now. We're measuring like this accessibility, how it behaves with population, like how many people are living in which type of areas, and to measure, and to understand better where should how the city is behaving and what's going on behind that. So that's what I've been working lately, and that's what I wanted to share today with you, and how we're using network tools and network science tools and a graph behind this to analyze, to understand, and to improve cities around the world. And last but not least, so I want to thank all my collaborators, because these are projects that have been, of course, developed together. And if anyone is interested in going more into the details, these are the 3 papers that we have published, where we have the methodologies and all the details that are behind these projects. So thank you very much, and I'm happy to take any question and to keep the conversation going.
Hi everyone. Today I would like to talk about content analysis with similarity graphs. But before I do so, please let me introduce myself. My name is Orsolya. I hold a PhD in cognitive linguistics. I'm also the co-founder of Crow Intelligence, which is a boutique consultancy specialized in AI and NLP. I'm also the co-founder of a Manning course entitled Sentiment Analysis and Natural Language Processing for Marketing. In both ventures, my partner is Zoltán Varjú. But so much about myself. let's focus on the talk. Let's see the aim of the presentation. First, I would like to demonstrate to you the versatility of similarity graphs. More precisely, that similarity graphs are applicable to various content analysis tasks. So you can analyze any kind of content with the help of similarity graphs. I will show you two cases, namely a text summarization task and an image analysis task. I would like to demonstrate, on the other hand, that similarity graphs fit multiple modalities. Again, in this case, I can only focus on text and images, but believe me, there are other modalities that they are good for. And finally, I would like to introduce you some practical tips on how to generate and fine-tune similarity graphs. In this way, you can get to know both the theoretical part or theoretical side and the practical side of similarity graphs. Let's see the outline of this talk. First, we will see what similarity graphs are. Then we will turn to the applicability of graphs, namely, what are they good for? And as I mentioned before, I will show you two examples. One of them is how to build similarity graphs of text, and the other is how to build similarity graphs of images. The talk will be closed by a summary. First, let's see what are similarity graphs themselves. If you have already heard the word nearest neighbor graph, then it means that you've heard a synonym of similarity graph. It is a variant of KNN. It is a KD3 or ball-tree data structure. Basically, what happens is that we find the key nearest vector, the key nearest for each vector. So basically, we draw an edge between the vector and its nearest neighbors. The weight of the edge can be the Euclidean distance. If you use Python, then the scikit-learn neighbors can help you in this task. So much about similarity graphs themselves. Now let's see what they are good for. On the one hand, you can model any kind of structure, so the similarity of any kind of entity. In our case, we will see how they can be used for text and images, but you can also model genes with the help of similarity graphs. In this way, by modeling these entities, the connection of these entities, you can get a deeper insight to the connection of any entities. So it's important, and I would like to highlight this fact that similarity graphs are not only used for illustrational purposes, but also for highlighting some connections. So get a deeper understanding of the connections of these entities. So in this way, you can find patterns of your data. You can get to know your data better. We will see that if two or more entities are connected, it can be almost granted that these entities form two or more clusters, or they belong to the same cluster. I will show you an example for that. If you have ever felt that you got lost in a graph because this graph has hundreds of edges and nodes, then I can show you a really good practical tip how to narrow down your graph, how to navigate in a graph with the help of backbone filtering. With the help of backbone filtering, you can explore just the core connections, so the most important connections. I will show you how. Now let's see my first example, which is text analysis with the help of similarity graphs. One of our projects was about War and Peace. Our main aim was to get to know the summary of this quite longish book, and we decided that we will use graph and graph theory to make an extractive summarization or extractive summarizer, which can give us the short summary of War and Peace. There are many approaches to War and Peace, and one of them comes from Woody Allen. He said that I took a speed reading course and read War and Peace in 20 minutes. It involves Russia. Our aim was to get to know more about War and Peace, more than this sentence that it involves Russia. We will see whether we were managed to do that or not. Let's see the source of our project. As the data, we use War and Peace, so the book written by Lev Tolstoy in English, so we use the English version. You can find the whole book as a TXT file in Project Gutenberg. And then if you are familiar with NLP processes, then you can know that the first step is always data cleaning. So we got rid of the punctuation marks, and we got a pure text without punctuation marks, and we had all the characters lowercase. The next step was a pre-processing task for which we used NLPK. If again you are into NLP, you are familiar with this package, with the help of which you can do sentence tokenization and word tokenization. So we got the pure text of War and Peace with this method. As a next step, we built the graph out of the text. How? The idea itself is based on text rank, which is constructed for skipgrams. Centrality measure, usually PageRank, is used to find the most important words or phrases or sentences. It's up to you. It's your choice whether you would like to find the most important words or phrases or bigger units like sentences. We modify this idea because we know that we want to use sentences as basic units. So we use the sentence and we built the vector out of the sentence. How? Each and every word of a sentence was measured, and the average of the words was used as a vector. So it's quite easy to understand if two vectors are similar. Two vectors are similar if two sentences are similar, or if two sentences are similar, then it means that the two vectors will be similar. Basically, it means similarity of the grammatical structure, like I like tea and I like milk will be really similar sentences. So the vectors will be quite similar and they will be quite close to each other. So much about the theoretical background of building a graph out of text. If you would like to if you would like to know more about graph theory and network science for natural language processing, then I would recommend you to visit our blog, because there you can find 4 posts or 4 post series there. We wrote quite many blog posts on the topic. Let's see the steps of building, of how to build a graph out of text. So as you could see before, first you should vectorize all the sentences of your text. In our case, we used BERT, and the tool for that is a sentence transformer. So after vectorizing all your sentences, you can make a similarity graph out of the sentences. Again, if you find that you have too many vectors and you have too many connections, and if you feel that you get lost in this big wood, then you should distill the backbone of the graph. So you should narrow it down. And as a last step, we use PageRank to determine the most important sentences. Why? Because based on the most important sentences, we made our summarizer. So as a result, here you can see the first 3 most important sentences of War and Peace. Of course, it's up to you. It's up to your settings if you would like to know the first 100 most important sentences of the text. If you would like to build a summarizer with 2,000 sentences, then you can have these settings. So if you read these sentences, you can see some keywords like Prince Andrew or Hussars. So you can get some bits and pieces of the whole novel. So you will know some details of the novel, like it doesn't take in the 21st century, because you can be quite sure that Hussars and Prince Andrew didn't live or they don't live in our age. So I'm really sure that you will you can get more out of the text than what Woody Allen said about it with the help of our summarizer. So much about text. Now let's turn to images. So let's see how to build similarity graphs of images. In this project, we were interested in the prototypes of women, not the prototypes of women in general, but the prototypes of women in American advertisements and their connections, so how these prototypes are connected. The source of the data, the source of the images was the advertising archive. We used the keyword women's, so the possessive, as a search word, like women's fashion, women's humor, women's anything. And we narrowed down our search to the US because we wanted to know the prototype of women in America between the 1890s and the 2010s. And we scraped thousands of images with our own scraper. So that's how we got our own data. And out of these data, our main aim was to build the graph itself. So each image was represented as a vector. And again, the basic idea is that the more the images are similar, the closer they are. So that's how we can see the relationship of the images. Let's see the steps. Again, let's be more practical. So first we vectorized the images using ResNet 18. The tool itself was image2vec PyTorch. We made a similarity graph out of the vectors. Again, it was a huge data, so that's why we needed to narrow it down with distilling its backbone. And finally, to order the images, to see their relationship, we used PageRank. I'm not sure whether you could see the images themselves in this graph, but this was the result. I can show you a smaller part of the graph. You can see the connections here, and what was really important and interesting for me as an analyst is that the images that are connected belong to the same cluster, because in this content analysis project, we built a clusterizer. So we first clustered all the images. We built 7 clusters, and it was really interesting to find in the graph that those images were connected that belong to the same clusters. So that's why I told you at the very beginning that these methods can be used. I mean, graph building can be used as a complementary method for other methods, like for clustering tasks. So as an analyst, you can use graph analysis not only as an illustrative method, but also as an analysis, as a method for analysis. So it's time to summarize what I've said so far. You could see that graph theory and similarity graphs themselves can be understood as a single method for making your data more understandable. You can get a deeper insight into your data. You can compare any elements and features of your data, like in the case of images, we compared different prototypes of women with this feature, and it can be applied for multiple modalities like text and images, for example, and various content analysis tasks can be applied with the help of graph theory, like summarizing a text or just analyze images. Finally, I generalized the workflow for you. So this is a workflow. These are the 4 steps that you can use for any kind of data. So for text and images or anything, you should build, as a first step, you should build vectors out of your data. For this, you should use a pre-trained model like image-to-vec PyTorch or sentence transformers or anything. As a second step, you should build your similarity graph itself out of vectors, out of the vectors that you got based on the Euclidean distance. As a third step, I would always recommend you to do backbone filtering, because in this way you can get rid of the noise and you can get all the informative edges. There is a really good paper on this topic for which I gave you the source, and also you can read here the code for backbone filtering. And finally, you shouldn't forget about centrality measures, because with the help of the centrality measures, you can order the nodes based on their relationship. So much about content analysis with the help of similarity graphs. If you liked this presentation, then I would recommend you to follow us. You can reach us via GitHub or Twitter, or we have our own webpage where you can read hot topics of NLP and AI in our blog. In our recent blog post, we wrote about similarity graphs themselves. Thank you.
Hello everybody, I'm András Németh, the CTO of LynxAnalytics, and I would like to introduce to all of you LynxKite, our graph data science platform. I want this to be extremely hands-on. I didn't even prepare slides. That's why I'm starting from the LynxKite homepage, which should be a very good resource anyways for anybody who hopefully is interested and want to learn more and try themselves. And most of the time we are going to spend on a LynxKite interface, but very quickly, let me summarize what LynxKite is. So basically LynxKite, we call it a graph data science platform. It's basically a visual tool where you can put together analysis workflows which incorporate deep graph syncing and graph algorithms and operations. It's very similar to something like Data IQ or RapidMiner or SPSS Modeler, but the big difference is that the basic unit of abstraction is graphs. So whereas those tools would work with tables, LynxKite is mainly working with graphs. It can also handle tables. And this makes really graph data science much more smooth and efficient in LynxKite. So let's actually try it ourselves. Like whatever I do here, you can do also yourself. I'm going to use a public demo instance. I'm just clicking on this try cloud version. And this takes me to demo.lynxkite.com. Like I already logged in because normally it takes 1-2 minutes until the instance is spin up. But if you do it yourself, it will ask you to log in using a Google account. So once you are here, you are in a Jupyter notebook interface. You will see why it's interesting. We work very well with Python, but let's start with the UI. So I just click this big button, and actually let me go full screen for more real estate. And this is the LynxKite starting screen. I'm going to just create a new workspace, and I'm going to do some stock correlation analysis. So let me give this stock correlation as the name of the workspace. First of all, I need some data, and for this demo, I'm just going to pull in some local data. So I have a CSV file, stocks.csv, and all I have to do is just drag it over to the LynxKite screen. And I also have another Parquet file. I can also use that. Like in real industry projects, you would probably connect to some more production data sources, like you could use Parquet from HDFS, you could connect to Hive. If you already have a graph, maybe use Neo4j, and GDBC is also an important one. Like any classical database can be used as source data. So let's take a quick look. This is basically just some stock metadata, name, sector, ticker, and this one here contains correlation information. So which pairs of tickers have a price correlation, which means when one is going up, the other is also going up more likely, and what is the amount of this correlation. Okay, so we have two tables, and I was telling you that LynxKite is all about graphs, so maybe let's turn these things into graphs. All these things in the right-hand side are different operation categories, and first we will need to build our graph. It's going to be super easy. I'm going to use this first table as the vertices of the graph, and this just creates me a graph with each line in this table becoming a vertex, and all the columns of the table are becoming vertex attributes. So I have 505 vertices, all have these 3 attributes, and I have no edges. So it's a super boring graph. Let's make it a bit less boring by using the other table as edges. So I'm going to connect my boring graph. I'm going to connect this table, and I set up these things. Like the first question I have to answer is that what is the ID attribute on my vertices which I can use to connect the edges? I can use this ticker attribute. And in the edge table, I have to designate which column shows the source vertex. It's going with ticker 1 in my case, and which other one is the destination vertex, which is going to be ticker 2. Okay, so at this point, we have an actual graph. So now we have roughly 2000 edges, some more edge attributes, and maybe it's time to take a look at our graph. So I'm going to use a graph visualization, and without even setting up anything, I already get something like a sample of the graph. Basically what happens is that the system chooses a vertex automatically and shows all its neighbors. Like I already have some idea of, like, I don't know, the density of this graph and how it looks, but it's still not very good because I don't even know which stock is this. So I can set up visualization parameters to actually show attributes together with the visualization. So I'm going to use name as label and sector as color. So now it starts to make more sense. All these are financial companies, all the neighbors of this Allstate corporation, who is also a financials company. But I still might like to look at a company that I want to choose and not let the system just randomly show me something. That's very easy to do. I say that, okay, I want vertex, which is, no, not sector, sorry, which is the ticker is ROK. Let's pick a vertex for which this restriction is true. And indeed, I selected Rockwell Automation and I see all the neighbors of this guy. And I can also extend the visualization here. Like I can say that, oh, actually, let me add the neighbors of this guy. And now we actually finally out of the same sector setup. So this guy is in a different sector, all these are industrials, and he is in materials. So let me also add this guy to the centers. And now I get some reasonably interesting visualization, like these are some industry guys, these are some material guys, and this is kind of a gateway between the two groups. Let me apply my center selection so that the system remembers that I want these three vertices to be used for neighbor selection. And let's try to add something like a graph metric. Like we can ask LynxKite to compute the importance of the different vertices based on just graph structure. Like we can use just the most well-known one. We have like quite a lot of graph algorithms available, but let's just go with PageRank for now. I'm connecting the graph. I could set up some parameters, but for now the defaults are perfectly fine. This is usually the case. And in the visualization, now I can say that actually let's use this PageRank as the size of these circles of the vertices. And now you can see that indeed these connecting guys, which are on the boundary of the two industries, seem to be important according to PageRank. And for example, this guy, if I add him to the centers, we can see he doesn't even have any other neighbor than PPG Industries. It has very low PageRank, like obviously is not very important in this particular network structure. All right, let me show you one more thing quickly. Another way to look at this graph. Like it's nice that we can visualize things. It's nice that we can compute some graph metrics, but another common useful tactic is to ask the system to do a clustering. Like there is an operation called modular clustering. I'm also showing another easy way, like you can always search for operations. You don't have to know the category. I'm going to cluster this graph. Like basically, this operation is going to create these disjoint clusters in a way that as few edges go between the cluster and as many edges go within the cluster as possible. And I'm going to visualize this. Let's see. So this time I'm going to need a two-sided visualization because I want to show the clusters and the vertices in the same visualization, and I want to select. Actually, I want to show all vertices. It's going to be pretty noisy, so I'm not going to put any labels. I still want to show sector colors. And in this side, if I look at the clusters, I see that there are like 328 clusters. Like how is it possible out of 505 vertices? Well, probably there are a lot of very small meaningless clusters. And if I look at the size histogram, indeed I see that most of the clusters are in this very, very low size. So I'm also going to add the filter that I only want clusters which are at least 20 vertex large. I think that's probably good enough to take a look. Oh, I forgot to switch this on, that I actually want the right-hand side also visualized. And I also want to actually see not just one cluster, but I want to show all clusters. All right, so what happened here? Now we see that there are 5 clusters found by LynxKite, which are fairly large, and as you can see, these correlate quite well with A, the sector. Like these guys, for example, all in real estate, and they also typically go to the same area in the graph. It's interesting that the financial one is actually fairly distributed, which makes sense because financial papers tend to correlate with different other companies. There is maybe one more which is somewhat interesting, is this one, which actually connects the industrials and the materials clusters, like they are kind of grouped together. So it's like, as we've seen previously, they are very strongly correlated, and LynxKite find is that actually these make a group even though they are in a different sector. What you can also see is that there are a lot of these isolated points which are not very interesting and just makes the visualization very noisy. So let me show you how you can very quickly handle something like that in LynxKite. So I actually want to throw away isolated points. So to do that, I just compute the degree, which is just the number of edges connected to a vertex. And then in the visualization, I again set up a filter to say that I'm only interested in those vertices which has a positive degree. And doing that, I hopefully end up with a less noisy and more pretty visualization. Indeed, all the isolated points are dropped, and then the structure of the graph is much more clear, and the clusters are visualized quite nicely. All right, so this is the level I wanted to reach in building this workspace here on the fly one by one. But I just quickly wanted to show where this workspace can go if we have more time. And in the same time, I'm showing you another very good tool to get to know LynxKite. So try.lynxkite.com is a read-only LynxKite instance. So you cannot change anything, but there are a lot of pre-built interesting workspaces which you can play around with. For example, there is this stock correlation analysis workspace, which is basically very similar to what I started to do, but everything is more sophisticated and more stuff is done here. So for example, here I compute a host of centrality metrics, not just page rank. I do the clustering in a more sophisticated way, and I get into this visualization where I see the connection between the sectors and the automatically found clusters. And here in the bottom, I also do something very interesting, is using this centrality metrics as a feature in a machine learning algorithm, and compare that to doing machine learning without the graph features and with the graph features. And well, of course, I conclude that using the graph features helps a lot. I don't want to get into details, but feel free to check this out. Like, there are a lot of comments and explanations, and it should be easy to understand this workspace. So there is one more thing I want to point out, is the beginning of the workspace. Like, what I did is that I used data files, but actually, how was those correlation computed? And the fact of the matter is that we use some Python code to calculate the correlation between the different stocks. And as you can see, you can just drop this Python code right here in LynxKite and use this to create the graph, or you can also use Python code in the middle of a workspace. And this shows an important concept in LynxKite. Like, easy things, for example, computing PageRank is super easy. You just drop in a box and you are done. But more difficult thing or more custom things like creating a graph based on correlation is also possible, because you can always resort to using Python and do basically whatever you want. There is actually another way to use Python and LynxKite together, and this is the other way around. Like now we used Python from LynxKite, but you can also use LynxKite from Python. Let me quickly show that. So I went back to my previous workspace and let me add one more box. Let me actually try to convert back to a table the result of our PageRank calculation. It's actually very simple. Like everything in LynxKite, every part of a graph can be accessed as a table. And I'm just going to use this default query showing getting all attributes from the vertices, but I'm going to order it by PageRank. I don't need this persisted. And let's see the result. Basically, I get a table which shows that, okay, the highest PageRank guy is this healthcare company, and then so on, so on. Now, okay, but I was talking about Python. Why did I do that? Now, what if I want to do this from a Python code, or want to automate it or whatever? Then I can just select these boxes, press this magic button, and I actually get some Python code. So this Python code is exactly equivalent to the boxes selected. Let me show you. So I prepared a notebook. What this notebook does is just doing the data loading part, because that is obviously different in Python than in the UI. There I just dropped the thing on the workspace, and here I actually have to load it from code. It's very simple. Like what I did, I just didn't want to type this, is okay, I'm importing the LynxKite Python library, and I'm uploading the same files I did before using these commands. And now I add another cell and just literally copy pasting the code from the LynxKite UI. And I of course I have to run these cells as well. Okay, so what happens here is that I, of course, this code is not good yet, because it refers to inputs which I just loaded here, and I didn't change the part where it tries to use this data. So I have to change this input table to meta, and this other input table to this core. Basically, I just use the loaded tables in the code here, and now I hope I don't get any more errors. Yes, and what I got here, like the last variable in the derived code, is the result of that SQL box, and I can access this as a pandas data frame. So if I do this, I get back a pandas data frame. Like right now, I quickly show you, it's LynxKite is calculating. So now the Python code triggered this LynxKite instance to start working, to redo all the calculations. And then I get the same result that I got earlier, is the top, like basically all companies ordered by their PageRank. Actually, I ordered the other way around. So this is the smallest PageRank guy. And sure, I can change this. Like here, I just put a desk and rerun this. And then, of course, I get the right ordering. All right, so that's about it. One more last thing that I want to very quickly show, and for that I go back to Trey again. These workspaces can be complicated to explain or present to a non-technical audience, and because of that, we have a so-called wizard interface. So that's how it looks like. It's really like a step-by-step thing, and it's really designed to be consumable for somebody who has no data science or no technical background, like a business decision maker. It's really set up by the data scientist. I will show you in a second how it's set up. But what the decision maker gets is this step-by-step, on one hand, information, like, for example, you can look at visualization, read description, and so on and so on. But there is also an interaction possibility. So in this case, the outcome is a fiber network plan. Like this is the result. And actually, the decision maker can come to this step 5 and change some assumptions. Like, for example, you can change what is the cost of a meter of fiber cable. Like if it's more expensive, goes back to step 6. you see you have a different optimum. Like now it is worth building less amount of cable. And this is just, of course, you could have multiple steps in which the user can set parameters. And behind all this is a normal LynxKite workspace. So if I open the workspace behind this, you will see that it's very similar to the previous one, like it's LynxKite boxes and stuff like that. But the data scientist creating this workspace just defined that, okay, from this workspace, I want to create this wizard, and explained what are the steps, which boxes are linked to each step. And for example, in this line, number 5, we actually link the parameters of a box to a step so that the user of the wizard can change things around. All right. That's all I wanted to quickly show, just to really give you a very quick overview. I hope you found it interesting. And if you did, then please try it yourself. Go to lynxkite.com, download it, try the demo, and reach out to us if you have any questions or issues. Thank you very much for your attention.
Hello, hi everyone. I'm András Vicsek, the CEO of Maven 7. And what I would like to talk to you about today is how network science can help you to speed up organizational change and also to improve collaboration. And to help you get the concept of all of this, I thought I would start with one of our case studies. A few years ago, we worked with a manufacturing firm, and they were experiencing all sorts of issues and problems regarding their internal communications. So a lot of gossips, problems in information flows, messages from the top were not reaching people on the bottom parts of the organization. So they asked us to look into what's happening in terms of information sharing and communication. We used organization network and analysis and a survey to map connections between the employees. So what you see here is the data coming from this or network survey, where each node represents an employee, and the connections between them are representative. They said that they receive information from one another around changes and informally. That's important to mention. If you look at this network, you already see that there are different parts of this network. These are actually different manufacturing sites with the different colors, and there are very central nodes as well in this network. And the question is, who are those people who become and evolve as central influencers in these networks? Who's, for instance, that person in the middle who most people receive information from around changes, informally again? And when we looked at the data, we were surprised because this person was not a top manager, not a director, not even a manager. He was someone from the bottom of the hierarchy. Who can this person be? Is it the secretary, or is it the driver who goes around the different manufacturing sites? Well, guess what? Actually, this person was the environmental health and safety specialist, which also makes sense because, these people are the ones who go around, train people, tell them, you should be wearing a helmet, and hey, watch out, don't fall into that hole, and these types of things. And by the way, he talks with almost everyone in the organization. So he's spreading one information from one part of the organization to someone else in a different manufacturing site. And why is this all interesting? Because research actually suggests that 70% of change initiatives fail to deliver expected outcomes in terms of growth, profits, efficiency, whatever was planned. It's just not happening. And what's cited is mainly problems with the immune system of the organization or the culture. So people don't like to let in new behaviors. It's pushed out. And also it's coming from the siloedness. So a lot of changes require communication and collaboration between different parts of the organization. And the more obvious one is problems in communication. So people don't understand why there is a need to change anything. And then how is that going to impact my work? And what do I need to do in this change as well? And still, most of the organizations, when it comes to deciding who will participate in drive this change, they look at their org chart. So who are the people, are managing different units, who are different experts. On the other hand, they don't know how people are influencing each other, how people are communicating with each other actually. So if you look at the difference between the formal and the informal networks that you see here, you see that in the informal network on the right side, you have Paul, who is the manager of one of the teams, who's not connected with his own team. Okay, he's connected in the top management team. And you see Liz, who's just someone from the sales team, who is not only hyper connected within the sales team, but also she's the one who's connecting the two parts of the organization. So when it comes to changes, who would be the one who you involve? Is it Paul or is it Liz? Probably you need to involve both, but you shouldn't leave out Liz, right? And our data from our research also suggests that influencers like Liz and the EHS guy reach 3 times more people directly through their trusted connections than top managers. So obviously you need these people when you want to drive change. Another important element of culture change is how behaviors spread in networks, not only through direct connections, but through indirect connections. The research from Christakis and Fowler says that social influence does not end with the people to who you are connected directly. It just ripples through these networks. What this means, for instance, is if I stop smoking, then it is 69% higher chance that my connections will also stop smoking. And this doesn't stop here. The connection of my connection will still be more likely to quit, and so is his or her connection. This is important because this means it really matters where we start the change, who are the first people who we involve in the change, who are the most connected, and who are most embedded in these networks, right? So how can we identify who the most influential employees are? For this, we use a two-factor approach. We focus on social connectivity and capabilities to influence others. For social connectivity, we look at who are the people who others turn to for advice, who are the people who others receive information from around changes, so specific social connections. But we also take into account the capabilities of others to influence. For instance, we look at people who others recognize for being innovative or for being motivating or inspiring for others. They might not be hyper connected. They might not be the ones who are continuously chatting with many people, but people look up to them, and through their recognition, they have an influence. For social connectivity, we use PageRank algorithm to identify social connection influence scores. For capability, we just use InDegree. Obviously, for social connections, as it's about spreading information, it's important to look at the indirect connections. That's why we're using PageRank algorithm. And unfortunately, capabilities don't spread in networks. So if someone is really good at math and I talk with that person, that won't make me a mathematician, unfortunately. Again, how is this used in real life projects? I would like to share with you one of our cases where we were working in the Irish healthcare system together with our strategic partner, Viral Change, headed by Dr. Leandro Herrero, how to change the culture in the healthcare system in a positive way, so that it becomes even more human, and the way people get the service in the healthcare system is really constructive. These were the behaviors they wanted to focus on. So you can say it's not values, it's specific behaviors, because it's hard to spread values. It's very conceptual. Behaviors can be perceived and can be taken on easier. My favorite one is, for instance, do we use names in our interactions and discussions with patients? If you use the name of the person, that already means that you're making that person look like a human, or you're looking at the person as a human being, right? So these were the things they wanted to change. And our partner Leandro Herrero, he was the one who was running the whole project. But before that, we identified the most influential people through this organization network analysis survey approach. We drew up the networks, we analyzed through the algorithms who the influencers were. And then he was the one who invited them to boot camps and workshops, where he worked with them on how can they influence these behaviors. What happens if they see that these behaviors are not happening, people are not using names, are not explaining what's going to be next in the treatments? How then can they jump in a positive way, or how can they provide feedback to their colleagues in a positive way? They also helped for them to recognize how they can actually give not only feedback to each other, but how can they use storytelling, for instance, to spread these new behaviors through these stories. And then what they saw after 1 or 2 years was that these behaviors really became the norm in the healthcare system. So this, using names increased by almost 50%. People explaining what's next for the patient grew by almost 40%. These are huge changes. You can imagine, like, healthcare system involves 100,000 people, and changing these behaviors is really difficult, because those are habits, how people work and how they see others doing things. That's why this was a really huge result. And then, what are the other things that networks can reveal about communication and collaboration? You can look at the network of an organization. You can look at the different teams indicated with different colors. You can look at where the influencers are. Already you might see that this organization seems to be siloed. So there's two components of this network split right in the middle. But you see someone seems to be connecting the two parts, probably high betweenness score, which can also be someone who is a bottleneck, because probably the amount of information that can spread from one part to the other of the organization is really limited. And also, this person can manipulate or distort the information as well. What else can you see? You can see brokers, who are people who are connected with different parts of the organization, who can really connect the dots. That's literally what you see here. But in other terms, for innovation, this is really important when someone from the technology part can be connected with someone who's more in the business side. And these brokers are the ones who can connect these key elements of expertise, for instance. You can also see different types of influencers, more like connectors, who are local influencers within a team, connecting people inside that team. And you can also identify communities or clusters in the network where people from different teams come together, work together effectively, which can be very valuable information if you want to set up new cross-functional teams, for instance. What else can you use the information and insights from net graphs and networks? One important aspect of organizational overall performance is collaboration, how different teams and different parts of the organization work together. You can generate insights on this using organizational network analysis. Again, bringing to you an example, we're working together with one of the global management consulting firms, and they wanted to bring broader knowledge to their clients. Some of their service lines were focused on providing certain expertise around let's say taxation. The other part was focused on providing services around advisory, and then the question was, can we bring those clients together, meaning can we bring that knowledge area to the clients by joining and connecting these people inside the management consultancy firm. And they also wanted to reward this behavior, rewarding cross-unit collaboration. And obviously for this, they needed objective data on a continuous basis so they can track the change of these networks over time. One other thing they wanted to do is they wanted to make sure that people stay connected so they can realize if somebody is disconnected from these networks, they can jump in and provide support to these people. And the obvious one is it is easier to sell to existing customers than to find new clients. So if you have people who help each other to sell to existing clients through bringing in new expertise by collaborating with others, then it's a highly the probability of generating more revenue is higher. How we did this is we created an application for them which uses email, calendar data, and chat data as well to identify how people are connected and strongly communicating with each other. And we created insights on personal level, like who are your strongest connections. You were able to see where you might need to build more connections, and also on a firm-wide level to see how are those business units connected, where are the gaps in terms of, we should have more communication between sales and marketing, and we see that it's not happening, or where are the connections which seem to be, generating collaborative overload because there's too much collaboration, too much communication going on. So in terms of what we discussed at this point, we looked at the role of influencers, how they can be used to spread information and spread new behaviors. We looked at the role of collaboration and how it's important to increase the performance of the organization. Now we're looking at the aspect of feedback in reinforcing new behaviors and values. For this, we developed an application which helps people who are working together to recognize and trigger behaviors, new behaviors and values and mindsets. How this works is, if I'm working together with a colleague and I receive an email from her, this sidebar pops up within my inbox, within the email, and I can recognize some aspect of her behavior because I see her as an energizer, for instance, and I can also provide some kind of comment which helps her to see this type of strengths that she has. And again, we're not only providing the feedback, we provide insights on these collaborations and communication on an individual level, and we can also provide information about the network. So because we're looking at the quality of these connections, we're able not only to see the frequency of the communication through the emails, but we're also able to see the quality of the collaboration between people who are actually working together on a continuous basis. To summarize all of this, what I wanted to highlight is that in every organization, there is an informal network that exists beside the formal structures. And that this informal structure, this informal network can be mapped through organizational network analysis. And this information can be used to improve the efficiency of managing change, speeding up change, and it can also help to improve collaboration between teams and inside teams. And it can also help to build a feedback culture for the company or the organization. Thank you for the time, and I will stay with you for the discussions, and happy to connect with you anytime. Thank you.
Hi, my name is Paco Nathan, and this talk is graph-based data science. It's actually it's a subset of a larger presentation, and the full slide deck is online here at this URL. I'm super excited about this topic, something that's been bubbling up, and really what I've seen in practice over the past, I'd say about 7 years, are a lot of indications toward leveraging graphs and graph-based approaches for data science. So a little bit about me. I made the terrible mistake of studying something that people warned me against in grad school back in the 80s. I did a lot of work in AI. In particular, I dived in for about 7 years doing neural networks. Also, people warned me away from that. Just wasn't going to go anywhere, And that included some hardware accelerator work in neural networks. During the AI winter, I ended up involved in a lot of network engineering. And of course, if you've done that, it's probably pretty close to the hardware. And I ended up as a guinea pig for this new thing that later got announced as AWS. One thing led to another. I led a really large head of instance on EC2, leading data teams in industry, leveraging these kinds of cloud compute resources very early on, and then eventually joined Databricks and taught thousands of people about machine learning and data engineering, things like this, with Apache Spark. Here are a few events of interest. I'll just throw these out as some background. These are kind of tangential to today's topic, but certainly come into play and will more and more. AutoML Summit has some fantastic videos. There's tutorials for doing RLib reinforcement learning, hands-on if you want to get started with that. Ben Lorick and I recently did an industry survey about NLP use, and it turns out that knowledge graphs are the #4 reason for NLP use cases in industry now. There's the KG 101 tutorial that Francois Scharf and I ran late last year. Metadata Day is highly recommended. It's about the practices at Netflix and Lyft and LinkedIn and others in response to GDPR, but now they're seeing a lot of graph-based approaches in their daily operations. And also the responsible AI in practice out of Gradient Flow that was with Raman Chaudhuri and others, a really interesting discussion, plus some upcoming. Okay, why graphs? Well, the thing is that graphs are everywhere. And, connected data sets have been around for a long time, although with the rise of relational approaches, data warehouses, that kind of thing since the 80s, late 80s specifically, people really didn't manipulate the graphs directly. But now we're seeing this as a need. And also a lot of capabilities have come out thanks to deep learning and cloud computing and others. So nearly every tech giant, whether we're talking about Google or Microsoft Bing or eBay, LinkedIn, Apple, Zalando, Amazon, all these, they use large-scale knowledge graph practices, first and foremost for content discovery, recommender systems, that kind of thing. So it's directly at their customers. If you go over into manufacturing sector, large companies working with supply chain and manufacturing, Bosch, Siemens, BASF, General Electric, etc. Certainly in a broader context of data governance, responsive GDPR, CCPA, things like that. LinkedIn, Lyft, and others, as I mentioned in the metadata day event. And then you go over into like drug discovery, a lot of healthcare applications. AstraZeneca and Johnson & Johnson, of course, they've been in the news because of COVID research, and Optum Health also really interesting work with graphs for their AI applications. Certainly in the financial sector, you see Bloomberg, what used to be Thomson Reuters, now Refinitiv, and most definitely in terms of the large consulting practices, especially for their audit and compliance divisions at IBM, Accenture, Capgemini. Now, one of the drivers of what's going on, I really love this lightning talk from Uli Sattler. We were in the same track doing lightning talks at ISWC this year. Uli was talking about how, machine learning has exploded, but the knowledge management side of things has really also exploded, although maybe not in the same exact applications. What we need going forward is to leverage all the work on machine learning along with all the work with taking advantage of human domain expertise. And this is a path forward. So hybrid solutions is what I'm really interested in. And there's good reason for it. I love this talk from Neil Thompson. There's an interview with my colleague Ben Lorica, but Neil Thompson's at MIT and doing a lot of mathematical analysis as well as economic analysis and really some of the physics that are involved once you get down to the hardware side. Deep learning is great, a lot of great applications. I love it, but we are hitting decreased marginal returns pending some sort of phenomenal physics breakthrough. And we have to look at that because there's a lot of intense energy and policy and climate implications of this. Check out, Neil Thompson has a one-pager describing this. It's really great. So complex AI workloads require complex graphs, and we must leverage machine learning models along with domain knowledge. For a long time, there's been a lot of intense graph work inside of SQL engines ever since SQL got started, but it's always been hidden inside of a sort of black box solution. And a lot of the graph-based libraries are highly balkanized, and frankly, some of them have a lot of legacy code. On the other hand, we know from the last decade of working in data science, working with data engineering solutions, particularly looking at things like Spark and Kafka and others, that functional programming, of course, came in, actor pattern and applicative systems. All of that came in to leverage neural hardware, and it took advantage of a lot of advanced math. And we have a long way to go in terms of working with graphs, leveraging exactly these learnings from a decade ago in big data. And this is just ideal for work with Ray, Rapids, etc. So I've been involved in this project, and I'm grateful we've got a collection of developers from different kinds of verticals, different use cases, helping out on this. Here's the repo, the docs. There's a survey. We'd love your feedback. There's an online tutorial, a lot of Jupyter notebooks that describe what you can do. There's a forum on LinkedIn, Graph-Based Data Science. Please join that. And also, I really make a point that we've got a glossary so that we can describe clearly what are our shared definitions. It's super important in this kind of field, especially when you're working in something that's inherently interdisciplinary and involves a lot of integration. Also, pointing to primary sources for a lot of these kind of definitions and terms. Where did it come from? What were they really talking about? Okay, and there's five-fold motivations. As I mentioned, the graph libraries are largely balkanized. So getting them to speak a kind of lingua franca is super important. Getting that to speak fluently, data science work in Python. So, does it work natively with Pandas, scikit-learn, PyTorch? And then on the other hand, does it work efficiently with big data tools for data engineering, cloud computing? Again, such as leveraging Parquet and Spark and Ray and Rapids, that kind of thing. I got into this. I've done a lot of work in natural language, and so I started this project, KG Lab, because of some work on spacey pipelines, PyTextRank and others, so that we could have knowledge graphs to help guide entity linking and really optimize a lot of the natural language understanding work. And again, striving toward hybrid AI approaches, merging the symbolic with the numeric and leveraging both. I believe that Gartner's calling that composite AI or something. Now, there are some pain points when you work with graphs. Number one, the wide body of semantic technologies, it started a decade before big data really got going popularly. And even though a lot of code is, from the past couple of years, it still looks like stuff that was written in 1994. So it tends to look a lot more like, it was built by people who think that XML is a good idea. So the code looks like HTTPD, and a lot less like something that's much more contemporary and leveraging the math and contemporary programming languages. Algebra is something that I would cite as really well written. There's a lot of interesting uses of graphs plus ML, but unfortunately, there's a lot of impedance mismatch between the graph libraries and the data science tools, and likewise between the graph libraries and really efficient distributed systems. Again, the data engineering practices. And frankly, graph databases are great, but they don't solve that problem. A lot of the hard stuff is integration. So this work is relatively agnostic, and we try to integrate with graph databases as much as possible. But really, we're at a layer up above. So graph theory, don't be scared. When I used to teach a related lecture, an earlier version of this, 7 years ago throughout industry, there's this notion of algebraic graph theory. So you can do a transformation between a graph and what's called an algebraic object. We use that as a general case for vectors, matrices, tensors. And it used to be, years ago, if I would say the word graph or I would say the word tensor, people would run screaming in the opposite direction. And nowadays people go, oh, tensor, yeah, you're talking about neural networks. Yeah, we're talking about neural networks and other kinds of complex graphs. But the important thing is you can transform mathematically between these sort of algebraic representations that are great for number crunching and the complex graphs, which are great for actually capturing the entire context. Now, this route of shoving everything into a matrix and then number crunching, it's generally called factorization. There's some really excellent people working in this field. I highly recommend David Gleick's lectures out of Purdue. It really breaks it down and explains it. Tim Davis at Texas A&M runs the Sparse Matrix Museum. I've got a screenshot there of just a fragment of it. If you do any kind of data analytics work, whether you're in Python or R, or MATLib or others, you're running Tim Davis's code. Really fascinating work. This has been going on since the early 60s, though, this idea of let's just shove it into a matrix and then number crunch. But realistically, one must blend the symbolic with the numeric. And while graph algorithms and the number crunching requires numeric representation, deep learning included, there are other things that really, really require the symbolic side. When you're working with natural language, human in the loop, when you're representing domain expertise, when you're struggling with fairness and bias and ethics and explainable AI, when you've got regulatory auditors coming up about compliance. So we need to marry the symbolic with numeric. And in KG Lab, we do that through mathematical transforms with our class library, going from a knowledge graph to a subgraph to a matrix or tensor or vector. And, this is nothing terribly new. I mean, it wasn't available for graphs, but in scikit-learn, when you have text data, you work with label encoders. And in PyTorch, you work with embedding. So this idea in general is about taking sections of your data set, your graph data set, vectorizing it to become dimensions. And importantly, also having the inverse transforms. Oddly enough, when you do this, it improves how much you can leverage distributed systems. So this is very important for the data engineering side of things, making them run effectively on the cloud. Now, in general, stepping back, looking at data science process, we're perpetually managing dimensionality. There's this general sense of moving from a lot of different unstructured data toward more and more refined, iterative refined structure. And the structure we take advantage because that's where we get features. That's how we build models. So in a data science workflow, typically we iterate through identifying low order embedding, and we refine that. We use those features across those dimensions. And this is how we build models, how we explain models, etc. Alternatively, what the cloud giants are selling right now is take your data, dump it into a trillion parameter transformer model, state-of-the-art inference, and then just hope, pray, and beg that your organization doesn't get audited or sued. ... Profit. So part of the thesis for graph-based data science is this idea of managing dimensionality and having that kind of transform, inverse transform between the symbolic and the numeric. Very key point. If you want to look at some primary sources about knowledge graphs, definitely one of my colleagues, Juan Sequeda, has an article coming out in Communications of the ACM next month, and there's a draft version of it, Brief History of Knowledge Graphs. Also, there was a survey paper last year called Knowledge Graphs by Aiden Hogan and about 20 other people. There's a really great paper, Ontology 101, that was written 20 years ago, the foundational paper in ontology by Natasha Noy and Deborah McGinnis. And really, rolling the clock back, Charles Sanders Peirce is arguably the most prolific scientist in US history. Founder of the USGS, and for that matter, he invented semiotics decades before Saussure. But he had a manuscript called Existential Graphs in 1882. They really broke this down. I'd also recommend a lot of great articles coming out of Dan McCrary on Medium. Dan is from Optum Health. So yeah, we can talk about graphs in the sense of semantic technologies, RDF and OWL and SCAS and all that great stuff. When you talk with graph database vendors, you're probably talking about property graphs. And the two are different, although they can be reconciled. There's the proposal out for RDF star. And definitely KG Lab takes the view of being able to reconcile between both of those. I'll show how it involves Parquet. So, my sense is, why not both? Our integration roadmap, it's a lot of work. Integration is hard, but it's really valuable. And it does, get involved in a lot of fields like data engineering and data science and natural language and graph algorithms and probabilistic graphs and visualization, et cetera, et cetera. So let me show just briefly a bit about using KG Lab. We talk about triples, sort of this grammatical construct of how to build graphs, where you have a subject through a predicate linking to an object. The subject and the object are nouns. The predicate is a verb. The predicate is defined in some sort of vocabulary, which is, your schema, your ontology. And so we talk about managing vocabularies as namespaces. That's kind of a big deal. There are things called playgrounds. These are typically websites where you can cut and paste some data, metadata, and see how it works. So here's an example using a data set off of Kaggle where, we've got a lot of recipes and just a few lines of code. We can instantiate a knowledge graph object, give it a couple of namespaces for ontologies. And then here's a recipe, right? We've got a link to its definitive URL. We say basically what kind of data object it is, what cooking time, 3 different ingredients, etc. Now, serialization is a hard problem in this space. And again, this is where some of the legacy problems come in, legacy code problems. This stuff was originally written by people who liked working in XML. And we're trying to bring it in the 21st century. Turtle is a good format. It's very human readable. And here's an example of serialization. KG Lab has spent a lot of time on hardening serialization and bringing them up to speed with using things like FSpec and Codex and pathlib and URL path and those that you need if you're going to be doing a lot of work in the cloud. There's also JSON-LD. It's popularized by Google with schema.org. I mentioned Natasha Noy. It's used for web page markup, which is fantastic to have knowledge graph data out in web pages all over. It's used by Facebook for fact checking. Virtually any JSON library can read this. Maybe not write it, but can read it. There's a playground. And really, a couple of lines of Python, you can convert one-to-one between all of the RDF kind of formats and JSON-LD. So they're interchangeable. And through some of the library integrations, we've got a host of other GraphML and Dot, and you can do YAML. There's some cool stuff going on. We've just integrated, actually just got finished on CSVW, so you can import CSV over the web. RML we're working on for mapping rules coming out of relational databases, things like that. But having said that, Parquet is the real news here. Parquet is order of magnitude more efficient, hands down, across the board, compared with any of these other formats. And Parquet gives you sharding. So it's a real natural for distributed systems. And it's native for Spark. It's native for Presto, now known as Trino. It's native for working with Cassandra and Kafka and on and on. And it leverages arrows. So that means that you can do a lot more faster processing, especially when you've got GPUs. Also, there's the ability by using tools like Presto and Spark and Iceberg, you can do predicate pushdown. And so this means that we can go into multiple orders of magnitude performance increase over those other formats. This is the way to go for data engineering with graphs, hands down. Visualization, wow. This is a whole other universe. We've got native integrations with PyBiz, Cairo, Matplotlib, of course. You can export out to tools like Gephi. But the thing is, just a few lines of Python, and you can do this transformation from a large complex graph, knowledge graph, through a subgraph into a tensor, and then build your visualization. And that was something that was hard to do before. Querying. In this world, Sparkle looks like SQL, but it works on graphs. So here, what we did was to make it speak pandas natively. And or you can get a name tuple iterator, and the literals are converted not as XML schema, but as Python wrapper. Shackle is fantastic. It's shape constraints. It's a way of having really easily read rules that can describe essentially unit tests for validation and prescription of what's going on. Auditing, you can use it for some form of inference as well. Really fantastic. And then there's the whole slew of graph algorithms, right? NetworkX and iGraph. I'm showing a centrality measure here to filter out what are the most popular ingredients. It's basically PageRank under the hood there, right? And then there's another constellation of inference. And the big thing that I want to say here is there's a lot of things to do with inference. Some of them don't handle uncertainty very well, but they're very formal as far as analytic solutions, like axiomatic work, inference, OWL, stuff like that. In the other quadrant, you can do graph embedding with deep learning, which handles uncertainty, not very analytic. And then there's others in between. So you really want to mix and match based on the use case. And here's an example of using 5 rules to do a data quality check on some annotations within a graph. Really important. Embedding. This is one of the ways that deep learning comes in with graphs. And here's an example of doing some data prep for your raw text data before you convert it into predicates and whatnot in your graph. This was just using GenSim, although we're working on Node2Vec and a few other libraries too. Okay, I only have a minute to go, but in general, data science process, we go through a lot of steps, a lot of data prep, a lot of feedback through every different part. Now, this is a worked example using 250,000 recipes, semi-structured text data, but it has some connections, relations that are inherent. We use this through many steps in KG Lab in the tutorials to build up a knowledge graph that you can leverage for, Rexis and discovery, that kind of thing. And there are a lot of steps along the way where, again, you mix and match these different techniques, whether you're doing deep learning for data prep or you've got human-in-the-loop feedback, you've got some data quality checks with Shackle, you're using graph algorithms like Leiden and K-cores, on and on and on, until you get down to the point of having a graph, you can really leverage the features, the dimensions for doing a recommender system. And the thing is, if you can do this with a recipe, then you can do this with an industrial process and a lot of other verticals, right? So I wish you well on graphs. I'd love to talk with you. Here's some ways to catch up with me. Thank you very much.